Is that the meeting?
Yeah, go on. I shall see you later.
Okay, thanks very
I
much.
think you are muted at the moment.
Sorry?
Hello, can you hear us? Just click that, then they'll hear you, okay?
share with us a second, folks, with a technical hitch with our online attendees? Stay away from the camera. What's happened? Okay, we're ready to roll, folks. Sorry for the slight delay. Giving us very close to the technical difficulties right. So I've got the great pleasure of chairing our first session this afternoon, and the first speaker, as you see, Luciano Pettinero, is going to talk about 30 years of the fractal universe debate. Luciano.
A lot of pocket
And
back.
this we plug here. It's okay? Can you hear?
That's working.
Yes, and then
Very good.
that somewhere.
Thank you. And the
then this.
yeah. And the clock to check how much time I take.
Over to you, Luciano.
Okay, thank you very much. It's for me a great pleasure to be here, really, for many reasons. First, I've been debating this stuff for 2 or 3 decades. And usually I'm on the side of the large structures, why people say, oh, everything is smooth. Coming here, everybody of you has made the discovery of some structure at least 500 megaparsec. Even Alexia overdid it with the rigs. So here I feel on the other side, you have turned the table around. Now, it's not that I'm defending the homogeneity, but I feel you are more extreme than me in saying that things are not smooth. In any case, what I will try to do is not to bore you, tell you a story with some interesting points, I hope. And then what has been the debate for years, I pick not to make a long history, but the interesting points when 2 areas collide, collaborate, interact, and they grow eventually. So this was my experience. I'm a physicist, mostly condensed matter, even though I worked also on general relativity and so on. But I like when different fields interact constructively. For example, physics, chemistry, mathematics have been defined as they are now in the late 1700s by the Napoleonic reforms and the Illuministic revolution. So these ideas, just one by one, they are not really up to date. So it is normal that there are, the problems today somehow our interaction of disciplines. You can see artificial intelligence, for example, is that physics, mathematics, and so on. And here we find something similar, even though it's all within physics. We have the cosmology that, you know, the only solution you have is Friedman, essentially. So you like if it is homogeneous. On the other hand, once you look at complex structure. How do you make sense? So you try to say they're not so complex, they're not so big, and push this story, but then these complex are bigger and bigger. So we have to change the actors of the game, of the play. I mean, the structures are the essence and not a mistake or something to put under the rug. This is my opinion. And then the structure have their own rules. They are very different. They are qualitatively different, and so on. And we have to make a new story, and that's the adventure of science. I like this statement of Steven Weinberg, with whom I had the pleasure of discussing. He was at one of my debates. I mean, he was present. So you see, he says, this is in the first book of 72. In the second book, in 2008, he says something similar, but I like more what he says here. He says, there remains the possibility that the universe is not homogeneous and isotropic after all. The real reason, though, for our adherence to the cosmological principle, whatever it is, you will see I have my own vision of this, is not that it is surely correct, but rather that it allows us to make use of the extremely limited data provided to cosmology by observational astronomy. We are in 72. If the data will not fit into this framework, we shall be able to conclude that either the cosmological principle or the principle of equivalence, this is a new concept, principle of equivalence, is wrong. Nothing could be more interesting. So I think you guys share this view because you are finding bigger and bigger structure, and they are the novelty, and they will be the future, in my opinion. Now, what is especially interesting, it's an interesting time because DAISY first release is beautiful, and there will be discussions on this. It pushes the fractal property even further, but I will not enter. Other people will show in detail this. There will be also Euclid, and in a few months there is a second release of DAISY. So I believe these two experiments, these two new data, will bring us to a new situation, extremely exciting. What has happened in my perspective, in these years, you see, is the confrontation of two fields, you know, statistical physics and complexity on one side, and astrophysics and cosmology on the other. At the beginning, you have angular catalogs. Now, angular catalogs correspond to a projection, but projections are very, very dangerous to draw conclusions. For example, the shadow of a cloud is compact. You know, is not with holes, the shadow. But the cloud is fractal, 2.4 dimension. Zones are not compact, but the shadow is compact. So taking angular projection is even more complex because you mix angles. So drawing conclusion what is up there in 3 dimensions from what you see from an orthogonal or an angular projection is extremely dangerous. In any case, at the beginning, one only had angular catalogs, and they look very smooth, obviously. And then, okay, what do you do if you want to study the fluctuations? You go to the library, and you find nice books on liquids, fluids. So liquids are obviously homogeneous apart a few angstroms, so a few tens of angstroms, and so you find the 2-point correlation function. It was not invented by Jim Peebles. It was invented over centuries by the fluid people. There, the problem of homogeneity is not the question. Obviously, normal fluids are certainly homogeneous at very small distances. So that function is okay if you have a situation where it is obviously homogeneous with the little fluctuation that the atoms don't penetrate and interact a little bit. So it was natural to do this. But over time, you know, people started looking at 3-dimensional stuff around the 80s, okay, CFA 1, 1, 2, Sloan. And then the situation got a little more complex because, you know, this story of the smooth stuff was problematic. And that's where I somehow came into the game. I mean, not only me. So you see, in physics, there was small fluctuation, but then there was a big revolution, which is, you know, chaos, second-order transition, renormalization group. All this put the complexity into the forefront, I mean, was not a problem, was the most interesting point. And then came fractal geometry, etc., rare events, etc. So at this point, the interaction was the other way. People on my field, Mandelbrot, me and others, we looked a little bit at this data and we say, but this you cannot do with the two-parameter correlation function and with the standard analysis. You have somehow to use different methods because it's a qualitative difference. You know, if you have a power law behavior, as they observed already earlier, if you have a power law behavior, this has a deep influence on the properties of the system. It's not just indicates a little bit slower, so we have to wait a little bit more. It's a qualitative difference that requires another qualitative thing. So what we are today? Today we have more and more evidence that the large structure are more the rules than the exception, and I think we have to be aware of what are the new methods or the best methods to characterize them. So this is a bit my philosophy. It's very interesting, by the way, and exciting. Now, maybe I want to make a comparison, you know, with an interesting analogy with economics. In economics, it's very similar than cosmology. People like smooth things, so they start with Gaussian fluctuations to estimate risk, for example. But fluctuations in economics, they also have the big data, I mean the big events. So you have the big crash that is never predicted by economic theory. So it's a very similar story. You like smooth things, Gaussian fluctuation, you make a theory, Black-Scholes theory, and then it doesn't work because there is always a bigger crash than before. 2008 crash was not predicted by anybody of the standard common wisdom people. So it's interesting that people in different fields reacted in a similar way. I mean, you like smoothness because that's mathematically simpler, but when it doesn't really work, there is an inertia to accept that the big fluctuation is there and is not a rare event once in a very while. Then, so this situation is a bit oldish, so you will forgive me, but it's always real. I mean, then it lacks the most recent development. So, okay, you start seeing, you know, three-dimensional stuff, CFA1, CFA2, etc., and the large structures were not expected. However, the cosmic microwave radiation is very smooth, indeed. But consider it is a projection, it is an angular projection, so even that one has to be careful. Okay, so we have these two things. We have to put together something very smooth, that is the microwave radiation, with something that begins to be rather clumpy, which are the three-dimensional distribution of galaxies. And this is the problem of structure formation, which led to dark matter and to inflation, etc., etc. Now, new things are, okay, the Planck, that you know better than me, Sloan pushed this story even further, and then also detection of individual very large things. So inhomogeneous becomes a very popular concept, and the metrics with the void, like Tolman-Bondi, you know, there is a place there is a center of the universe, but may replace dark energy in the acceleration. This I've seen in some of your work also. Somebody thinks that the void may give an acceleration that doesn't need dark energy. I think this is very interesting. I share the interest in this vision. Okay, now, there are many reasons to think of universe is homogeneous. Cosmological principle in its most trivial point of view, that all points are alike, you will see there are other visions one can make. So in this perspective, a non-homogeneous universe is inconceivable, but this is a misconception because, for example, in a fractal, you may have the conditional cosmological principle. A very point of the system, so galaxy, is similar to any other point of the system, but you have a symmetry breaking between the points of the system, so where is matter, and where is void. So void-matter symmetry breaking perfectly compatible with the one step more sophisticated cosmological principle. Then, okay, Friedman metric is the only exactly solvable case, but you know, nature doesn't care how good we are as mathematicians. I mean, because, for example, also for the atoms, we can solve exactly the hydrogen atom, but that doesn't mean that uranium doesn't exist. So we have to cope with our limits and not try to make the nature as to conform with what we can solve exactly. Okay, then the only problem is that when you look, there are many reasons to think it's homogeneous, but when you look, it is not homogeneous. How did it start? These are the very first three-dimensional data. This corresponds, it's also a projection, but it already gives you a glimpse of what is there in 3 dimensions. For example, it's a slice, so the projection doesn't distort much. It's like if you would travel in space, you take a slice and you look at it. So the projection is limited effect. So the CFA1. CFA1, already showed a certain clustering. And people looked at it. For example, Mandelbrot, was a good friend of mine, he saw it and he said, oh, this must be fractal. But then people say, you see fractals everywhere, which was true. But in a way, fractals are everywhere. Your lungs are fractal, your neurons, and many other things. So it is not so inconceivable that the universe is also fractal, but maybe and maybe not. We have to study it. Then there is CFA1, CFA2, etc. At this point come the three-dimensional analysis by mostly Jim Peebles. So three-dimensional analysis always use the two-point correlation function, the one that tells you essentially the fluctuation from the average. This is a crucial point, fluctuation from the average. So the average has to be there. In a fluid, the average is there. And the basic criterion is to define a crossover to homogeneity is the distance where the fluctuation is of the order of the average. So you may have a very large correlation nearby, then it slowly decays. When it becomes of the order of the average, you say, well, then after this, more or less, we have the average. This is the criterion. Now, this criterion is correct if the system has really a crossover to an average. But if it does not have a crossover to an average, you will always get some distance, but that has a different meaning. This has been my technical comment to this. What they found was that this length defined from where the correlation function somehow seems to give smoothing is that it is 5 megaparsec for galaxies and 25 for cluster. But clusters are made of galaxies, so how can it be that galaxies become homogeneous before the cluster, but the clusters are made of galaxies? So this was a puzzle. Okay, and this was, they were supposed to be precise numbers, with 2% errors. So what happens then? You see, these were the data at the time I made the famous Princeton debate in '96. So there was, I will tell you more. But when the data became more and more, this story of the 5 megaparsec became embarrassing because 5 megaparsec is the size of this pixel. So this is this little square is 5 megaparsec. Do you believe that this stuff is homogeneous at this or twice or 3 times this? There's nothing to do, obviously. So Mandelbrot said, obviously, this is a fractal universe. But then they said, you see fractals everywhere. We have made the careful mathematical analysis, and we show that this stuff is compatible with homogeneity at 5. When I saw this, I reasoned the other way around. If you have a mathematical analysis that given this picture, it shows it's homogeneous at this size, it means that the mathematical analysis you make is wrong. This was my position. So I went to see what they were doing. And I want to mention important people for me in this path. The first person who showed me galaxy distribution was Roland Coopers, who was an undergraduate student at the University of Groningen, where I was professor in my youth. And Roland finally didn't work. I think we wrote a little paper, but he became a top manager at Shell, the Dutch oil company. But somehow he showed me a Scientific American CFA1 or CFA2, and he said, don't you think this could be fractal? So this is really the responsible for all my travel in this field. Then, of course, I was a very good friend of Benoit Mandelbrot, and we discussed this a lot. But the very first person who was being professional astrophysicist, he collaborated with us, was Paul Coleman, who unfortunately is not with us anymore, and he had very bad sickness some years ago, even though he was very young. But so he was the first professional guy in astrophysics who helped me in developing these ideas. So I thank all these 3 people very much. So what is the problem with the correlation function? You see, this is the standard correlation function. it is clear what you do. You do density, density. So if the system is homogeneous, this density, density is just the square of the average, so C is 0. If the system has a correlation, so you have groups of things, this means that at small distance, this is much bigger than the n average square. So if you have that the Xi is bigger than 1, or Xi minus 1 is bigger than 0, and so you have strong correlation. Then when Xi becomes 1, you say the fluctuations are of the order of the average, so you are decreasingly going to the average. This is the criterion for defining this R0. But there is a problem. You see, in a fluid where things are more or less like this, so you clearly have a constant conditional density, so up here, density correlation function is perfectly constant, and it has some wiggle at small scale. But suppose that you have something like this, a power law. After all, they saw a power law for at least on one side of the function. Then the problem is, what is your average? You see, and if you normalize, for example, here, you have a catalog as deep as this, you have a certain average. But if your catalog is deeper, you have another average. So the question whether you have a well-defined average is a crucial point if you have system with long-range correlation, which clearly are there because you have power law, at least on one side of the function. So you see, you cannot decide with this function if the system is homogeneous or not. You have to use other functions. This is not just changing the function, because clearly if you have Xi, you also have the conditional density. But it means changing the attitude. I mean, complexity is a subtle thing. And power law imply fractal, imply long range, imply clustering. So it's not just, let's see, a little bit farther, it must become homogeneous, so who cares if it is a power law? If it is a power law, it is a qualitative difference. And so looking at a different function means you have to change your mindset, not just changing the function. Okay, let's have a look at the fractal. This is the simplest fractal I could produce for you. You see, a fractal is a system where you have self-similarity. So the structure that you see at small scale, you see, is similar to the structure that you see at bigger scale, and so on. Suppose we have this system. What do we observe? Well, if we compute the conditional density, you see, from every point of the system, the conditional density will decay. Because if you are here, when you go at R2, you have these 5 points in a very small volume. Then you have 25, but in a much bigger volume. And then you have 125 in a much bigger volume. So conditional density is always decaying from every point. This is absolutely anomalous. If you have a smooth distribution, this is impossible. So this is a non-analyticity property. So it's a complexity property. It's not something just changing the function. Okay, so each point of the structure is statistically similar to any other point. And this, we already can go to a new version of the cosmological principle, I mean the conditional cosmological principle, in which voids and occupied points are not symmetric. Then, if you do the conditional density, you see you have this, that if you do it for points of the system, for example, the blue point, you have a conditional density that decays, as I described before. If you take the green point, you have a similar behavior. But if you take a point in a void, you see, before you start measuring anything, you have to reach cluster. So at the beginning, you have 0. Then you jump because you enter a cluster, and then you align with the other things. So there is a basic asymmetry between voids and occupied zones in a fractal. And eventually, the voids will dominate, because eventually the structure is asymptotically empty if you take it mathematically, I mean, ideally. However, so the voids are always there, and there is always a big void near you, as there is always a big cluster near you. This is the non-intuitive vision of the non-analytic structure, like a fractal. So what I did in '87 was to make a little exercise. Suppose I have an ideal fractal structure, where you saw the conditional density decays as a power law. Okay, this is the depth of the sample, if it is a sphere or whatever. So it's just, this is the number of points into a certain volume. And okay, no, this is the fractal, this is the volume, okay? Then I compute the two-point correlation function. And you see the problem is that the density, conditional density, depends on the depth of the system, on the size of the system. Then when you do the condition that xi becomes 1, you see you get that this characteristic distance is linearly proportional to the depth of the system. You see, so you will always have a point where xi is 1, but if the system is really homogeneous, then that point is related to the real homogeneity. If the system is a fractal or something with long-range correlation, you will get a number because it has to go through 1, because xi is normalized, the integral is 0. So it has to, if there is correlation, it has to go to 1 and to 0, but then these numbers just are a fraction of the depth of the sample. Now this, I was very shocked to get this simple result because it permitted to understand a number of puzzles. So you see, these are two. We are talking about ideal fractal structure. If I have a fractal structure of a certain size, I get this type of xi of r. If I have a deeper size, I have this other type. So you see the amplitude of the function depends on the size of the system, which is not something nice to have, because you would like to have something intrinsic, not something that measures how big is my telescope, okay? So you see, so the problem is with this function, you cannot decide whether you have homogeneity or not. This is the essence of the story. Just to make it clear once more, you see, standard interpretation of two-point correlation function is okay if the sample really becomes homogeneous. But if it does not become homogeneous, this xi will give you totally spurious results, which have nothing to do with the property of the system, but they have only to do with how big is the system. Okay, now this is the most important point of my lecture. Okay, and what I could see in the 80s was that this famous xi of galaxies and clusters, they remind very, very much what you see in a fractal with different depth. This is the ideal fractal. I mean, they just shift. Okay, so maybe this shift is that you are observing a fractal structure, and not that you have really those numbers as real homogenization. In fact, these two numbers were different, and they proposed the luminosity segregation, which is the cousin of dark matter. I mean, something very weird. I don't tell you how it was described, but this is a mathematical misconception that was explained with the physical assumption. Now I think all this can disappear once we do. Okay, these are other cases in which you cut the sample at different depth, and you see that there is a shift of the correlation function. Now this is an example of what I mean, that they cannot be different, the correlation length, because you see, on one hand you have galaxies, individual galaxies, but some of these galaxies are part of cluster when you make the cluster. So it is clear that the clusters are more luminous, so the depth of the catalog is bigger. How much is bigger? Exactly 5 times. So you see, this could resolve perfectly well the mismatch 525. So the interpretation that different catalogs with different depth at different amplitude was considered a noise. You know, you have one sample, another sample, but it was not a noise, it was scaling. The density was just scaling with the power law, and it was giving this effect as I described. Okay, so in summary, so from the analysis of galaxy and cluster, we are late 80s, galaxy aggregating complex structure, with the scaling properties. The dimension is about 2, etc. The usual correlation is only valid, 5 megaparsec is an artifact, and the galaxy cluster mismatch is automatically solved, and you don't need luminosity segregation. So a new picture emerged, which was profound implication for experiment simulation theory. So this story got reasonably popular. So Neil Turok and other people at Princeton, on the occasion of the 250th anniversary of foundation of Princeton, they decided to make a especially big meeting, Critical Dialogues in Cosmology, 1996. And the idea was to have debates on the hot subject. The first hot subject was, is the universe homogeneous or fractal? See, by Mark Davis and Peebles, who was there, and me and my collaborators. Now, this was very hectic. So they made it in the mathematics hall, which was bigger. There were 400 or 500 people. Phil Anderson, you know, the Nobel Prize, a good friend of mine, was not allowed to enter because it was so crowded that the fire police said, you cannot enter, etc. So I had to go to him after the discussion to tell him what happened. So it was really a hectic moment. And then, okay, I presented my arguments, and in the end, I mean, I would say it was the opposite of now. Now I'm talking to people who discover 1,000 megaparsec. There, people really believe that 525 were the real numbers of the universe's smoothness. So we made a bet officially, is in the proceeding. The bet was between Davis and Peebles and myself, that according to them, this value represents the real characteristic length that indicate the real crossover to homogeneity. According to me, this length has no physical meaning, and they are just a fraction of the effective sample size. They will increase with deeper sample. Okay, now, I would say the bet is over by far, but I never heard any more these guys. I mean, maybe I should tell Neil. Neil Turok was the organizer. He argued this. So after the Princeton debate, our story got rather popular. So there was a very nice journalist, Amanda Gefter, who is probably attending the online. So Amanda, thank you very much. She was working, she's still working in New Scientist, and she followed all this fractal debate. And over some time, they made the cover of New Scientist. Then we wrote a monography, etc. So the story got popular. So the story, and people got scared. I mean, now what happens to the homogeneous universe? We have to defend the homogeneous universe. And what more than the royal astronomer is the person to defend, you know, the holy grail of the homogeneous universe? So the royal astronomer Martin Rees decided to intervene in person, and he did it with this paper. Now, you see, this was a little bit after, a couple of years after the Princeton debate, but it was motivated by that, basically. Now, the problem is, what does he write? He writes that at short distance, short distance is fractal, but then slowly, when you go farther, maybe not 5 and 25, but 100, 200, it becomes smooth. But he had the problem. Because, you know, he had the problem because I have shown that if you use the two-point correlation function, that is not any proof. So he had to argue, but most people, everybody uses the two-point correlation function. So you see, on one end, he acknowledged that he said, in recent years, Pietronelli and co-workers argued that most analysis of density fluctuation had assumed larger scale homogeneity, but they have no, you know, proof. It was just a self-consistent assumption, but it doesn't show that it is homogeneous. So he had a big problem to argue that somebody had used my method, my way of looking, and still get that it is homogeneous. But nobody did this except one person, Mr. Scaramella. You see, he says, the latest result of Scaramella provide the closest fractal measurement yet to homogeneity. Okay, interesting. Who is Scaramella? Do you know Scaramella? Why isn't he here? Because he made this big discovery. You know, this saved the Nature paper of the Royal Astronomer. Scaramella is an astronomer at Monte Porzio Observatory, Rome, you see. So after this Royal Astronomer Nature, you see, the universe becomes a Roman affair. There is Sapienza, where we argue the universe is fractal, and Monte Porzio, the Scaramella argues the universe is homogeneous. How is it possible? No Harvard, no Cambridge, no Lancashire, nothing. It's Rome. Outside the raccordo anulare, inside the raccordo anulare. It's all there, as always has been. So Scaramella came to me one day, and he said, oh, I'm seeing your stuff. I want to learn your method. So I spent 2 afternoons with him. And he said, I have this ERA data. I have some data. I want to learn your method. So I use your method to analyze our stuff. Because, you know, at that point, our method was pretty popular. We had 2 covers of Nature, of New Science, New Scientist, and so on, the Prince. And all. So he was curious. And he came to me twice, and I told him how to do. Then he said, oh, once I have done, I come back and we discuss. Since that day, I have still to see Scaramella again. I've never seen him anymore up to today. What did Scaramella do? He did a lot of tests, and more or less they looked like what I claimed. But then he found one magic point. You see, we have to go back to the Royal Astronomer, because the Royal Astronomer says, you see, Scaramella pointed out the importance of appropriate corrections. These are the K correction to the spectra. These spectral band corrections are crucial to approximate, etc., to do. So, K correction. Now, this is a Scaramella analysis. So, he played with these K corrections, which are not something, you know, like the Schrödinger equation. You have a couple of parameters, and he found that playing with these parameters and also doing my way, you could push the dimension more towards 3, okay? Now, all the other tests he made, they gave the fractal result, but this one with the playing with the K correction, somehow he gave a good result. I mean, for him, that it was smooth, it was three-dimensional. The problem is that when we saw this paper, we continued to play with the K corrections. And you know, we found that if you want, you can get dimension not only 3, but also 4, 5, and 6. So with the K correction, you get whatever you want, because you distort the behavior and you know whatever result you want to get. And obviously, what do you do if you are minded that you have to find homogeneity? You decide that the right K correction is precisely what gives 3 dimension. Now, he didn't have the courage to come with me in person and discuss this stuff, so he just published this little paper, which, you know, gave him the popularity that for the Nature paper of the Royal Astronomer, this was the proof that the universe was homogeneous. Probably you didn't know, guys, but so you are learning. This was 90-something, 99. Now, you have to know that the Royal Astronomer has certain duties. One of the duties is to inform the Royal Court about the most important results in the field. And you know, what more important than the Scaramella paper? Because it proved finally that the universe is homogeneous. So this is the Royal Astronomer who is exposing to Her Majesty the Scaramella paper, but unfortunately, as you can see, the expression of Her Majesty is not fully convinced, because she knew that things cannot be so silly as the K correction. So these were the 5 minutes of glory of Scaramella. And okay, let's go to another subject. So as you see, we have to have a little fun. I hope you are not offended. Greatest respect, okay? But I thought this picture was so beautiful, I couldn't resist to show it to you. Okay, there are other problems with the long-range stuff, etc. One problem is, once I worked out this simple analysis, if you have, you know, I'm talking why the CMBR is moot. Okay, I have still time. So CMBR is moot because the potential fluctuations should be constant. They should not grow with scale, otherwise they would destroy. So suppose you have a Poisson distribution, okay? You play, it's a little exercise. You play with the Poisson distribution and you compute the fluctuation of the potential and the fluctuation of the temperature. Now you see, if you have a Poisson distribution, the fluctuation of the temperature grows with the square root of R. I don't know if you know this. When I work it out, I don't find this much in books. But you know, this means that a Poisson distribution, random, cannot be compatible with the fact that you have a smooth radiation. You knew this? I mean, to me, it was a big shock. So you have to assume that the original distribution of matter is more than random, like glassy, is compact, not like Poisson. And in fact, when you see this type of graphs, so okay, just to tell you an idea, give you an idea. So if you have random is this. This is like the rain on the ground, okay? Then you have a fractal, is this. So when it's random, the power law is P of k is constant. When you have a fractal, it is decaying, okay? When you have super homogeneous, this is like a glass, means that there are really no voids, it's compact. Then you have P of k that goes like this, that you need to have that the radiation is not disturbed. I'm not sure whether I'm going too fast in this, but what I want to say is that the fact that the radiation is isotropic, if you believe it, that before decoupling it was together with matter distribution, implies not that the matter is random. It implies that the matter is super homogeneous. This to me was a big shock. I mean, I offer to you this idea. I mean, so you see this part here, which you are familiar, this means that it is super homogeneous, so random is not enough. So this is another point. I didn't work on this, but to me it is disturbing that the universe at the beginning is not even random, it's more than random, super homogeneous. It's a point I don't know how to explain, but I can tell you this is necessary unless the radiation would be disturbed by this. Let's go to another argument. You see, even independent on theory, if you think how do you build structures, you see there is the following problem. You know, the fluctuation, the peculiar velocity of galaxy is this much, I learned from you. Then the time is this, and so simply you make a small structure, 1 to 10 megaparsec, unless you think the structure are there from the very beginning. But just there is no time to make big structures. So this is a big problem, I think, independent on the model. Okay, then one can argue, okay, there are large structures, but they have they may have small amplitude. This we have checked, so it needs another story that is long to say, but so we have checked that it's not only that the structures are large, but they have also important amplitude, and still, if you take into consideration this, you still get a fractal. Okay, I'm almost closing. Very good, thank you. Last couple of points. So people argued, when Amanda Gefter interviewed us and the American groups about the fractal universe and the homogeneous universe, one of them said, well, but after all, who cares about visible matter? I mean, visible matter is 3%. We have 90% of dark matter. Dark matter is homogeneous, while Pietro Nero thinks that even the dark matter is fractal. So Amanda phones me and says, do you think that the dark matter is fractal? I say, I measure things, I don't dream. So I don't say anything. I say, but they really say that you think that it is fractal. I say, but anyhow, they convinced her to write in one of the the New Scientist paper that I think that dark matter is also fractal. And they say, so this is obviously wrong. Now, after a couple of years, the lensing showed that dark matter traces visible matter, and it has large structure. So Amanda wrote another paper, and he said, as predicted by Pietro Nero, dark matter is also fractal. Okay, this is the imaginary prediction I made, because they say this to accuse me, it finally turned out to be right. Okay, funny stories. Okay, so also dark matter. Well, you need a new theoretical approach, etc. This we can discuss maybe. But now, let me give you a new vision of the cosmological principle. You see, fractals are interesting and fascinating, and not something to put under the rug, something to be fascinated. And, so maybe they will, lead us to a complication from the mathematics, but also to something very interesting. So considering that, you see, in a fractal, in a way, every point is at the center of the universe, which seems, I would say, in Italian we say ossimoro, something that is opposite meaning. Because you invoke the cosmological principle to avoid to have a universe in the center. But this is, it turns the story the other way. You say everybody is at the center of the universe, so it's even democratic. Now, if you look at, because after all, from every point, you have the same power law behavior that drops down. So this could mean that Lemaitre-Tolman-Bondi is a good approximation. And, after all, if you have this game that to explain the 3-4% of baryonic matter on which we make experiments, you need 97% of dark stuff, I think it may be worth to have a look at the fractal vision if one can improve a little bit the situation. Okay, this idea was already somehow put in action, so the use of Lemaitre-Tolman-Bondi, and we, some couple of years ago, even more, we proposed that this could replace the acceleration due to dark energy. Reading what you do, I've read some papers, some abstracts, this idea that the void by itself, somehow also Wiltshire argues the back reaction of a void, this is the fractal story. I think it's the same story. So when you think the void can give to accelerated thing, it's the same story as the fractal. Okay. So I think we are in an interesting moment. I thank you very much for remembering me all this stuff in the past. As you see, I'm still fresh, even though it was some time I didn't debate this. This debate is the opposite. You have more big structure than I ever claimed, so you are the other side. But I enjoy very much discussing with you, and I wish you good luck for your job and your discoveries. Thank you very much. Let me thank, okay, these are the people who collaborated with us. Thank you very much, Luciano. I'm sure you all are absolutely fascinating. I'm sure there will be questions. Who wants to go first? Please don't be shy. That's part of the reason keeping this meeting quite small, so we could have plenty of discussion. Who wants to do it? Go ahead, sir.
Okay, I start. Luciano, thanks for the talk. So two points. One is more like a comment about the CMB. I don't quite understand your problem because the CMB is generated by a plasma. It was which was homogeneous and isomorphic. That's the idea, and so it's really a plasma. And so, in that respect, I don't see where your problems come from with that.
Okay.
But the other question is.
No, but let's say one at a time. Okay, let me answer this. No, because this. So, right is a plasma. What are the properties of this plasma? Is this plasma a Poisson distribution, random, or it is more packed like a solid or a glass or a liquid? Consider a Poisson distribution would be a gas. The air in this room is Poisson. This object is not Poisson, it's compact. My point is, suppose the plasma is like the air in this room, Poisson. The fluctuations would scale, the potential fluctuation would scale like the square root of distance. So at large distance, they become very large, and they would destroy the isotropy of the radiation.
I understand all of this, but the thing is that the physics of that plasma is super standard physics, well-known, quantum scattering, electrons and photons, and basically nothing else. So I don't see why this has not been analyzed more in depth, in a sense, so that you can solve it. The other question is more like you present a picture of the distribution of galaxies, and that's fine. Why there is no attempt in, because after all we believe in the expansion of the universe, and that there was this CMB which again is generated through completely standard physics, very, very well known. So there must be a model to build a fractal structure that grows through gravity, because that's the other thing. The only long-range force that we think is acting is gravity. Why there is no model to generate this fractal structure from a starting point which is super homogeneous, as you say?
Okay, well, this would require 1 week to answer because I don't know the answer. Okay, of course, I ask this question myself, but I've done part of the story. Okay, now you show even bigger structures than me, but I put the emphasis that the things are not so smooth. Okay, that's I think, and that CFR cannot be a proof of anything. So you have this problem. You do have it. Okay, but this was not the subject of my talk. But since you ask, I give you my speculation. Indeed, this is a big question, okay? How do you make such big structures? Are you sure that gravity is the only way? For example, consider before recombination with radiation, etc., there is a recombination of matter and antimatter, which gives the asymmetry of only 10 to the 9. This is the story. There was matter and antimatter with a small asymmetry. In this enormous process of recombination, maybe you make filaments by the recombination process, not by gravity. This is something I would consider worth exploring. So something that leads to fractal structure already before. Because as you have seen by my back of the envelope calculation, if you consider the anomalous velocities and the time of the universe, there is just no time to make big structures, but they are there. So in my opinion, it is conceivable that at the time of recombination, z equal 1,000, the universe was already fractal. But then you say, but then how is it possible? Because I mean, if it is fractal, the radiation must fill the fractal. Well, not exactly. Suppose you have matter and antimatter that recombine and leave at the end a little structure of matter which is fractal. Most of the space will be void. So most of the matter-antimatter reactions which leads to the photon, they will happen in the void. That's why it's isotropic, not because the other is moot. Okay, I don't know whether, I'm thinking at this question with this type of speculation, which I've never written down, so you will not criticize. But okay, if I have to answer, but obviously I don't know the answer. But let me put it this way, in order to get the answer, first you have to put the right question. So I think what I've done is I helped to try to put the question in the proper terms. But obviously it's an important question.
Other questions?
Can I just make a follow-up comment to, which might clarify Bruno's question and what Professor Pietro said about the distribution being super homogeneous. This was already remarked on by Edward Harrison in a paper in 1962, that Poisson fluctuations cannot be responsible for the structure you see for the reason that you gave.
Yeah.
The scaling is wrong.
I didn't claim it was a discovery.
Clarify his,
yeah.
So hence the Harrison Z2 spectrum, which has nothing to do with the Poisson fluctuations. They have the right scaling. Of course, the basis, the justification for that was purely empirical. You must have that spectrum, otherwise you have too large anisotropies or too many black holes at the other end.
Exactly.
But that avoids that problem of the scaling, which, as you correctly said, is characteristic of Poisson fluctuations.
Thanks.
So, a question over here.
Yeah, so just a remark, so in defense of Scaramella, he is one of the authors of the discovery of the Shapley supercluster, right? You know about it? Huh?
I don't know.
So Shapley supercluster, it's a concentration of 28 galaxy clusters, and it is so heavy that it participates in our motion in the universe at 2.3 billion kilometers per second, and it's beyond the great attractor.
I appreciate, and I suggest that he goes to the Royal Astronomer and say, I was wrong, and you too.
So it's quite ironic. Yeah.
Okay. I mean, you know, I hope you see this is all a joke. I mean, everybody plays the game, and so I like to be a little bit theatrical. I mean,
I have a quick question,
please.
comment. Over the years, like all of us, I've given many public lectures and public talks, and I always talk about structures, and now these days we talk about filaments and voids and what have you. And then I talk about the cosmological principle and how on a large enough scale everything looks homogeneous. And I've had the same question many times over the years of every time astronomers seem to think the universe is uniform, they find out it isn't. So why do they still hold on to the cosmological principle?
Well, because it would be nice and simple. I mean,
Simple.
Well, you know, it's the only solution you have of general relativity. After all, you have to write papers.
I can tell I said something heretical because there was a shocked look over the whole of the audience.
But I think you guys believe in the cosmological principle traditional less than me, which to me is a new situation to have.
There was a question a bit further back there. Yes, please.
So I'm wondering what are sort of signatures you would see of the fractal universe on other elements of the structure or the structure of the cosmic web, so the filaments and walls and voids. Are there sort of specific features you would be expecting or specific sort of distribution characteristics?
Not really. I think in order to answer this question, you have to have a model. and I really don't. But I think this will be, in my opinion, you know, the fractal has to substitute the homogeneous. What we see is a piece of fractal mostly. But even suppose, even long ago, people said, oh, maybe at 100, at 200, now you will see with Daisy, it's even 400, where it may stop. But even if you have, let's say, the fractal stops at 100, suppose, it's a very conservative view today. But I mean, this must have an effect on the metric. So the question is, can you compute the metric of a fractal? Okay, and I believe in this sense, I will start using the method of Tolman-Bondi. But one of the points I skipped, not to take too much of your time, but this question makes me to think again. So you see, it's very difficult if you have Einstein equation to put the fractal in T mu nu on the right and derive the metric. But a smart guy from Brazil, Elcio Abdallah, do you know Elcio Abdallah? Okay, I was impressed. He wrote a little paper which is totally useless, but I think very smart. He said, suppose I invent a metric. I plug it into the equation on the left side, and I compute T mu nu. So he invented the metric, ultrametric. Ultrametric is the same metric that you get in a spin glass, if you are familiar. So it's the metric of a tree. You know, when you are on a tree, the distance between two leaves is related to the point where the two branches depart. This is ultrametricity. You can write easily a metric like this. It has nothing to do with the universe, but just I thought the idea was brilliant. And then from an ultrametric, you find the distribution of matter that corresponds to the ultrametric. It is not really fractal, unfortunately, but it is homogeneous with some particular peculiarities. So I believe smart people like this guy could open up a new vision. So guess what could be the G mu nu of a fractal and try to reproduce it on the right of the equation. Okay, for example, this, if a guy would do this, you know, playing the game the other way around. But, you know, this is the problem. So we cannot put it under the rug because we cannot solve the mathematics. I mean, I'm accustomed not to solve mathematics. I have worked 20 years on high temperature superconductivity, and I went to sleep every day happily, even though I had no solution. This is what I say. I mean, you guys, I mean, you as cosmologists, you always want to go, not you, this is a particular pleasant situation for me. No, it's for real, no adulation. You see, one day I met Silvio Berlusconi, who is expert in adulation, as you probably know. And there was a state meeting in Jerusalem. I had to sign science agreements, and he was there, I mean, with some ministers. So we had the same dinner. And then he said, you know, my father taught me something very important, that adulation, simple adulation, oh, you are very brilliant, you are very beautiful, that's not good. When you meet somebody, everybody has some good characteristics. Beauty, clever, well-dressed, I don't know, pleasant character. You must study and you must understand what are the real good characteristics of this person. So there is somehow an action. It's not just to say you are beautiful, you are smart. No, you have to know. And then you have to tell him or her what are the good things. So this is different from adulation. It's really, you know, you have first to study what is real and not just to talk empty. I found this very good, very smart guy. The only thing I appreciate of Berlusconi, by the way. But this guy was smarter than we all thought, by the way. Okay.
On that philosophical note,
yeah, I think we close.
I think we should thank our speaker again. Thank you very much.
Thank you.
We now have a 10-minute break with the opportunity to grab a coffee, take a comfort break. Hopefully there's biscuits.
I think there's some leftovers.
Some biscuits.
I think there's some fresh stuff at
and reconvene in 10 minutes.
It was a brilliant talk. Thank you so much.
Thank you. As you see, I really enjoyed coming here.
Yes, it
slides?
You can try.
Let me see.
Click into this window.
Ah, yes, I can. So everything works fine.
Good to
Okay, yes, perfect. Yeah.
Okay, thank you all for being good and coming back so promptly. Apologise that the break was planned so short. It wasn't me that made the timetable, was it, Alexia? Instead, I meant to say that if you have any questions about local logistics or what have you, the locals are the folk in the blue lanyards, and local students are the ones in the red lanyards. So if you ask someone in a blue or a red lanyard, local logistical questions, they should be able to help you. I meant to say that at the start. So our next speaker is Eleonora Di Valentino, and she's going to be talking about cracks in the standard model.
Thank you. Thanks a lot for the invitation. It's a pleasure to be here. Okay, so I'll start introducing the standard model in cosmology, that is the lambda-Goddard-Matter model. Among the various models proposed in the literature, this is one chosen as the standard model, mostly because of its simplicity, because it can describe very well the observations. But unfortunately, this is now I cannot see after the slides. Maybe that's better, yes. So unfortunately, this is based on 3 completely unknown quantities. So we need an early stage of accelerated expansion that we call inflation to produce the initial tiny density perturbations needed for structure formation. Did I do something?
Carry on.
Okay. Then we need a clustering matter component to facilitate the structure formation. We call this dark matter.
One of the students is at the back playing with another switch, isn't it?
Let me see if I can. Is that okay?
That's number 2 that we want.
That's perfect.
I'll move slowly.
Okay. And then
When I find out who it is at the back, is he in trouble? Just carry on.
okay. And then we have an energy component to explain the current stage of accelerated expansion, and we call this dark energy. Okay, among all the possibilities, we have chosen very specific solution for lambda-Goddard-Matter. So the inflation is given by a single minimally coupled Rayleigh scalar field. Dark matter is pressureless fluid made of cold and collisionless particles, and the dark energy is a cosmological constant term. So we have theoretical shortcomings, but in any case, we still consider lambda-Goddard-Matter the preferred model because of its ability to describe the observed phenomena. So this is what we do. Okay, we say that a flat lambda-Goddard-Matter is in agreement with most of the data, and if we look at the data, we see that this is a good approximation. So we have these are the CMB data, Planck, SPT, and ACT. And we see that all of them agree with lambda-Goddard-Matter. Then we have the BAO data here, and they agree with lambda-Goddard-Matter, weak lensing data, KITS, DES, HSC, and supernovae data. So, but what does it mean that they agree with lambda-Goddard-Matter? Because how we do the analysis in cosmology, we assume a model, and then we fit the data with this model. So in principle, every model agrees with the data. What we mean is that, first of all, the model is a good fit of the data themselves. And second point is we consider extension to the model. In order for them to be preferred, and taking into account the Occam's razor principle, they need to significantly improve the fit of the data because we are introducing some complexity. So at the moment, what we see is that the lambda-Goddard-Matter model preferred by the data is a different one for the different data sets. So in a few words, we are assuming lambda-Goddard-Matter, then we are analyzing our data, and the values, the parameters that we find is different for the different data sets. So we have small tension, and assuming lambda-Goddard-Matter again. And for example, between CMB and BAO, we have 2.3 sigma tension, increase from the first data release. On the value of the matter density between BAO and supernova, we are up to 2.9 sigma tension. Then we have, if we compare, if we consider a combination of CMB data, SPT and ACT, and the BAO data, always assuming lambda-Goddard-Matter, they are in 3.7 sigma tension. Then we have the old dark energy probes combined together, so weak lengths in supernovae, BO, and clusters. They are in 2.8 sigma tension with the CMB. And then we have an internal tension in the CMB themselves, because when we look at the paper, we always see a comparison between ACT and PLIC-PR3. PLIC-PR3 is the legacy release of Planck in 2018, but since then there have been new reanalysis and new maps called PR4, and if we now compare the ACT data with Kanspek and Hillipop and PR4, the tension goes up 2.5, 2.6 sigma. So now we can say, okay, this is not significant because we are in that regime between 2 and 3 sigma, so not really can call this a disagreement. But this is true because we are assuming lambda quarter matter. If we now look at the extension, the fact that we have these small tensions is producing some consequences on the extensions. And one that everybody is talking about in the last couple of years is this indication for dynamical dark energy that we have when we look at the combination of CMB data and the BAO data from DESI. Okay, so if we, instead of having a cosmological constant with an equation of state equal to -1, we parameterize the dark energy equation of state in this way. So W0 is the value of the equation of state today, and WA is evolution with time. This is called CPL parametrization and is some sort of Taylor expansion around today. We see that the quadrant preferred by the data is W0 larger than -1 in the quintessence regime and WA less than 0. So this indication for dynamical dark energy is 3.1 sigma only with BO and CMB. It goes up to 2.8 to 4.2 sigma considering different supernovae data. However, this is the results of last year in the DESI paper. Since then, there have been new recalibration of the supernovae data, and these are the latest results. So Union 3.1, Pantheon Plus, and DES supernovae Doveki, all of them, they have been recalibrated, and now they agree on the value of the indication of dynamical dark energy, so that is ranging between 3.2 and 3.4 sigma. So I think that we want to understand is that how much is this robust, okay? Because we want to see if this is due to the fact that there could be some systematics in the data. So a simple test that we can do is trying to remove one data set at a time. So we can consider different combinations, removing BO, supernovae, and CMB data. I'll try to lower the light again. And we can see, no, there's no way. And we can see that we always are in the same quadrant. So even if we don't consider all the three data sets at the same time, we always have an indication for W0 larger than -1 and WA less than 0, even if this doesn't go up to 3 sigma. Another thing that is pointed out, okay, but we have these constraints that are pointing towards the cosmological constant, that this is point here for W0 equal, W equals 0 and W0 equal to -1. So people said, okay, but this could be an indication that there is mirage dark energy. Mirage dark energy means dark energy that mimic the distances of the lambda quadrant matter model. But actually, what we see with the DESI data is that we have a phantom crossing. Phantom crossing means that there is a scale factor for which the equation of state is equal to -1. If this scale factor is equal to this expression here, and this aligns in this plane, so we can see that these constraints are actually along one of these lines. They are very narrow along these lines. So the fact that they are pointing towards the cosmological constant, it means that we have a very strong indication for a phantom crossing that is even stronger than the indication for the dynamical dark energy itself, so 5.2 sigma. So then we said, okay, but maybe it's a problem of the parametrization, because at the end we're using this parametrization here that is ad hoc, so we want to try different ones. We tested a few in the literature, JPP, exponential, logarithmic, and Barbosa-Alcanis. As you can see, this indication for dynamical dark energy is very robust using different parametrization, is always in the same quadrant, and all of them, all this parametrization have a phantom crossing at the same scale factor. And the one that is preferred by the data is not even the CPL, but the Barbosa-Alcanis. So we have something that is quintessence today as a phantom crossing, and then is a phantom in the past with the equation of state smaller than -1, but doesn't go really negative as the CPL, for example, but instead as a plateau in this way. Okay, So now we said, okay, but at this point, let's see if we can find a more general parameterization. So instead of choosing one, we introduce one new parameter, beta, and depending on the value of beta, this is going to tell us which one is the parameterization preferred by the data. So if beta is equal 1, we have the CPL one. If beta goes to 0, we have the logarithmic one. Beta minus 1, the linear parameterization. Unfortunately, the data are not good enough still to constrain the value of beta. So we have still indication for dynamical dark energy. We need all the data sets available to do this analysis, but beta is mostly unconstrained, so can be really in agreement with everything, with all the parameterization that we can test. Okay, another thing that we explored is the fact that from reconstruction we see oscillations in the dark energy equational state. So what we did is try, first of all, to reduce the number of parameters. So we consider parameterization with only 1 degree of freedom, reducing the number of parameters to just 1. We consider some models in the literature. And the one that is preferred by the data is something like that, okay, that has the phantom crossing always at the same time, is oscillating with decreasing frequencies and an amplitude that is decreasing with time, and today is very different from a cosmological constant. And this kind of model is preferred by the data using a model comparison even over the CPL parameterization. So now we said, okay, let's try a completely different approach. Instead of parameterizing the dark energy equation of state, we are going to change, we are going to Taylor expand the pressure of the dark energy. And we can truncate the Taylor series in the first order or at the second order. And then we introduce 2 new parameters, and this will be the new dark energy equation of state for these cases. So at the first order, unfortunately, we always have a pole, so we have a singularity in the dark energy equation of state. This is not well behaved. But in the second order, the phenomenology is very rich, so we can have always quintessence, always phantom crossing, several phantom crossing, and we can also have singularities. So if we now try this other parameterization, we see again that the indication for the dynamical dark energy is there at more than 4 sigma, and what is the best fit that is preferred by the data is again quintessence today, phantom crossing at the same redshift, is something that doesn't go very negative like the Barbosa-Alcanis parameterization. Okay, so at this point, last step was to understand if we can have a model-independent approach. So we can do a cosmographic expansion of the Hubble rate at the luminosity distance. Usually what is done is to consider the expansion for Z0 around today and Taylor expansion of Padé to 1, and then we consider higher redshift, but in this case what we decided to do is to do a Padé expansion for different value of the redshift in the range 0, 1. In this way we are Padé expanding exactly where we have the data. So when we are going to reconstruct the deceleration, the jerk, the snap parameters, this is happening exactly where we have the data, and we can gain up to 2 orders of magnitude on these observables. So now we compare with the lambda Goddard-Matter model, that is this blue line here, and then you have the CPL model, and you see the deceleration parameter also in this case is following something that a CPL dynamical dark energy behavior, so is above the lambda Goddard-Matter line today, and then goes below a higher redshift. And if we consider the OM of Z diagnostic that we expect to be constant for lambda Goddard-Matter, actually we see a deviation with redshift. So we are completing this agreement again with the lambda Goddard-Matter model. So the cosmographic quantities are by definition independent of the underlying dynamics. So these are conditions that every model of cosmic acceleration should satisfy. Okay, so now I started saying, okay, data sets are in disagreement, and their disagreement was very small, okay, between 2 and 3 sigma, and this is a consequence of the disagreement. So we have a strong evidence for dynamical dark energy. Are there any consequences? Yes, and unfortunately the consequences are on the neutrino mass, okay? If we now consider a combination of BAO data and CMB, we have an upper limit less than 0.064 eV at 95% confidence level. But we know from laboratory that the total neutrino mass should be larger than 0.06 eV at 95% confidence level. So we start to see a tension among these two. Can we quantify the tension? Yes, this has been done with the force release of DESI, so the constraints are slightly larger. But as you can see, CMB plus DESI was giving less than 0.064. If we add more data sets, if we have Hubble constant, galaxy cluster, gamma ray bars, cosmic chronometers, the upper limit can go can become even smaller. So if we now consider what is the tension between the cosmology and the laboratory experiments, if you assume a normal ordering, this is about 2.5 sigma, with inverted ordering is 3.5 sigma. And if this is why we want to be conservative, because for some dataset combination and some tools, statistical tools, we see that the tension is up to 5 sigma. So something is happening, okay? If we use cosmological data, we are in disagreement with laboratory. And if we let the total neutrino mass to go in the negative regime, we see that actually the peak is in the negative part. So a combination of BAO and CMB data is preferring an effective total neutrino mass equal to minus 0.1 EV. Okay, this is completely unphysical, it's impossible. So this is why we call this effective neutrino mass. But the point here is that we are assuming lambda good dark matter, and on top of that we are considering an extension for the total neutrino mass. So if we are getting the lambda good dark matter model wrong, this is why we cannot recover a value of the total neutrino mass that makes sense. And so if we try to change the lambda good dark matter and instead we assume again a dynamical dark energy, W0, WA, we see that the total neutrino mass moves towards the positive values. So this seems to be another indication that the universe is not lambda good dark matter. So we try to understand why, what is the physical property that is moving the mass of neutrinos to become positive again. So first of all, we reduced again the number of parameters. So we consider one parameter, dark energy equation of state, that have some characteristics that can help us understand if what we see is definitely a volume effect. So since we are increasing the volume of the parameter space, the neutrino mass is moving towards positive values, or there is something, a physical property that we need. So we try a generalized Tauin model that never crosses the W equal to -1 and does a rapid dark energy evolution for redshift less than 0.05. Now we try a generalized emergent dark energy, again doesn't cross W equal to -1, but has a reduced dark energy density redshift higher than 1. Now we try different calibrated Tauin model to change the rapidity of the dark energy evolution, and then the mirage model. And in this case we have a phantom crossing, and also we have for the rapid evolution also reduce dark energy density for higher redshift. And the models, the dark energy equation of state that work better are those that are reducing the dark energy density for redshift larger than 1. And this is happening for the mirage model and the generalized emergent dark energy. So it seems like what we need, okay, is something that is reducing the density at higher redshift, and this is what is giving an indication for a negative neutrino mass. So we can compensate this changing the model of dark energy that we are considering. Unfortunately, okay, both of them work to recover a positive total neutrino mass, but unfortunately the generalized emergent dark energy is not giving a good fit of the data because it doesn't allow to have the phantom crossing. That is instead a necessity when we consider a combination of CMB and BAO. Okay, so now I want to change a bit the perspective, okay, because these results, okay, weren't well digested by the cosmological community, so there was a lot of effort in trying to dissect the BAO and supernovae data to understand if there were systematics in the data that could explain these problems. I think there is a selection bias in the cosmological community, so they trust the data only when they agree with Planck lambda good dark matter, but actually also the CMB has some problems. The point is that we need large collaboration to reanalyze the data, and also they do a better job in advertising. So what are the CMB problems? First of all, the problem with the lensing. Okay, photons coming from recombination to us are deflected by the matter interposed. We can compute the lensing precisely if we know the model, So what we can do is to place an amplitude in front of the lensing, and of course we expect this to be equal 1. But we can measure this through the smoothing of the peaks in the damping tail. So if a lens is different from 1, we can definitely detect it, and this is an indication that something is wrong. And actually, this is what has been detected by Planck, okay, something larger than 1 at 2.8 sigma, the famous A-lens problem. And okay, this is again, so it's a consistency check that is failing, because this must be equal to 1, assuming lambda Godard matter. So if we find something larger than 1, we're in presence of systematics or new physics. And so again, it's 2.8 sigma, so we can say it's a statistical fluctuation, but this is producing then problems when we look at the extensions of lambda Godard matter. What are these problems? First of all, we have an indication for a closed universe, more than 3 sigma, because if we have a closed universe, we have more matter means more lensing, so we have this correlation between omega k and A lens. And since there is an indication for a curvature different from 0, now there is an inconsistency between Planck and the BAO data. This inconsistency is at the level of 3 sigma. So every time we are assuming lambda Godard matter, we are combining together CMB and BAO data, and these are as DSS BAO data, not a new one. We are combining something that is in disagreement. We are forcing the universe to be flat, and then we are combining their data, biasing the constraints. Another consequence is again on the total neutrino mass, because neutrinos are suppressing the structure formation for scales smaller than the free streaming scales. So if we have more massive neutrinos, we have less structure, so we have less lensing. But we found from the CMB that we have an excess of lensing. That means that we have an indication for smaller neutrino mass. So the fact that we have a negative neutrino mass is actually not a result of DESI, but is a result of Planck. If we have Planck alone, we peak in the negative region, and if we combine with the oldest DSS BAO data, again we peak in the negative region. So again, the negative neutrino mass is a problem coming from Planck, from the fact that we have an excess of lensing in Planck that is considered a statistical fluctuation, so it's fixed to equal to 1, and we have this kind of problem. Now, if we consider that A lens is instead a systematic in the Planck data, and we marginalize over this A lens parameter, we can move the total neutrino mass back in the positive region. And this is not something that went away with the latest data. If we consider a combination of Planck, SPT, and ACT, together with the new BAO DESI, we see that A lens is different from 1 at 3.5 sigma, and as a consequence, we have a total neutrino mass that is less than 0.048 TeV at 95% confidence level, well below the lower limit allowed by laboratory. Okay, so this is one problem, and but, as I said, there are the new reanalysis of Planck PR4 with Kanspec, and they claim everything is in agreement now with lambda Godard matter. But let's have a look a bit better what they are doing here. Okay, these are the temperature power spectrum, and you can see here that the two temperature power spectrum between the two releases are giving exactly the same amount of closed universe as before. So we are ruling out omega k exactly with the same uncertainty. So what is happening is not that the indication for the closed universe goes away, but what is changing is the polarization. So they change the polarization in such a way that now the average value is more in agreement with lambda Godard matter, but we are introducing a tension on the value of theta. Theta is the angular size of the sound horizon at recombination. That should be the value better measured by the CMB. So in this case, if we want to change the polarization so that the universe is lambda Godard matter, we introduce an inconsistency at 2.8 sigma on theta that goes up to 3.3 sigma when the length and omega k are free to vary. And this new lambda Godard matter model is in disagreement at 4.5 sigma with the data themselves. So if we take lambda Godard matter model and then we analyze the Kanspec data, we consider the reduced chi-square, and we see that the lambda Godard matter is not a good fit of the data at all. Okay, finally, last point about the CMB is the optical depth, okay? Because the optical depth is something very important in our analysis. It went down from the value of W up to the value of Planck significantly because of better understanding of the foregrounds, better measurement, better understanding of systematics. So now we have two ways of measuring tau, okay? Through the polarization bump, this is not, in the low E data, that is this one, that goes like tau square. And another way is in the damping tail of the temperature power spectrum convoluted with the amplitude of the scalar perturbation. Okay, so now these are the data where this value of tau is coming from. We take them, if we consider that all these are conservatively independent and Gaussian distributed, and instead of fitting them with a bump, we fit them with a straight line, we see that this is still in agreement with the data with a p-value of 0.063. If we now consider only the bumps of multiple 15, and we fit them with no signal at all, 0, this is in agreement with the data, is this red posterior here at 1 sigma. So this region here where is coming this very, very strong value for tau is in agreement with no signal at all, and is in the cosmic variance limited region. So if we are additional systematics at this additional foreground, and this is not right, we are getting wrong our whole cosmology. And now if we remove this low E data from Planck, and we analyze the data without this polarization data, we see that all the problems of the CMB I was talking about, A length, omega k, and W, they disappear. Everything is in agreement with lambda Godard matter, but tau should be something like 0.07, 0.08. And also the value of the total neutrino mass goes back to be positive again, because I said that this can be measured through the damping tail, AS, a to the minus 2 tau, but A length is doing something similar in the damping tail, so we have a strong correlation between the lensing and tau, and the lensing is affecting the value of the total neutrino mass. So if the value of tau is wrong, this is why we have such a strong upper limit on the neutrino mass bound. Okay, so now, yes, I'm rushing, I think I can do that now. Okay, so what we do usually in cosmology, we interpret the observation through our personal theoretical and historical prior. We call them robust if they agree with what we think is true. Otherwise, we dismiss them and question their reliability. So I'm not saying that we need new physics. I'm saying that we become too precise and not accurate enough. So, and also we are cherry picking the data depending on what we want to obtain. So we decide to use the old Planck data release, the new one, Pantheon Plus, the SY5, Desior DSS. So also BAO before were considered the gold standard, now it's questioned, we don't like them anymore. And in all of that, we are ignoring the elephant in the room, this is the value of the Hubble constant. This more than 10 years that we have a strong disagreement. So what is the Hubble constant? The Hubble constant describes the expansion rates of the universe today, and we can measure this in two ways. One is measuring the luminosity distance and recessional velocity on galaxies, and then computing the proportionality factor. This is the Hubble law. Of course, this is valid for very small redshift. At higher redshift, we need additional corrections, but this approach is completely model cosmological model independent, and is based only on geometrical quantities. The second way we can measure the Hubble constant is measuring something in the early universe, assuming a model for the expansion history of the universe, like the Force-Friedman equation for the lambda Godard matter scenario, and then infer the value of the Hubble constant. Okay, this second approach is more similar to measuring how tall is a little baby, then observe a curve of growth and predict how tall it will be when it will be an adult. If you're using the wrong curve of growth, for example, the one of a British boy for an Italian boy, you're not going to get it right. That happened to my son. Okay, so now if we compare these two estimates, we see that they disagree, and they become more than 5 sigma at the end of 2021 with the latest SHOES data release. So on one side, we have the distance ladder measurements, and on the other side, we have the Planck results, assuming a lambda Godard matter model. So what is a distance ladder? A distance ladder is something that calibrates objects that are more and more far away. So we can calibrate the surface that are pulsating stars with geometrical quantities, like parallaxes, detached decreasing binaries, and masers. Then we use this phase to calibrate the type 1a supernovae that are exploding stars and the nearby galaxies. And then the type 1a supernovae calibrated in this way are used in the Hubble flow to be able to use the Hubble law. And in this way, we obtain a value of the Hubble constant. So if the fit is done over the 3 ranks at the same time, taking into account the diagonal terms, we can have such a strong constraint on H0. On the other side, you have the CMB constraints. Okay, these were the Planck estimates assuming a lambda Godard matter model. But now we have other CMB experiments, not just Planck and W, but also ACT and SPT, that are ground-based CMB telescope. We saw already that all of them agree very well when we assume a lambda Godard matter model. And this is the value of the Hubble constant that we found on this side. So 67.24 plus minus 0.35 kilometer per second per megaparsec. But this is completely model dependent, as I said. So if we change the model, this can change completely. And we also have degeneracy between the parameters that can modify and can skew the result towards one direction. On the local side, instead, also we had a lot of improvement. So there is the new result from the H0 distance network collaboration. And now the tension is at the level of 7.1 sigma with the CMB results. So this is the situation. All the local measurements are preferring an higher value. And these are direct measurements, and all the early universe measurements are preferring a lower value, and these are assuming a lambda Godard matter model. So what has been done in this H0 DN collaboration is taken all these measurements, decompose them, and connecting them into a single coherent network. In a few words, we have different distance ladder in this way. What we've been doing is to connect them horizontally. So consider the correlation at the component level and creating a network to obtain a value of the Hubble constant. In order to do that, there was we organized a workshop last year at ISSI, and we invited all the people expert in distance ladder and expert in different measurements, objects, to come together, describe their work, and we voted on a baseline based on the maturity of the different measurements before seeing any value for the Hubble constant. So what should go in the baseline and what should go in the variance. And this is what we obtained. So we have the baseline, that is this value here, 1.1% accuracy. If we consider all the datasets together, the value is much higher and also much stronger, 0.9%, considering all together. But as you can see, all the variants are very, very robust. So even if we remove Cepheids, supernovae, we consider different kind of supernovae. So all of them are very consistent. The result doesn't really move. So it seems that it doesn't depend on any one source. It cannot really be attributed to one systematic or some conspiracy of systematics that go in the same direction or unknown unknowns. And we are able to recover all the results in the literature. So whatever is the value published, with this distance network, we can recover it. And combining them together, you see that this value doesn't really move. So at this point, what we can try to do instead is changing the model that we are assuming when we analyze CMB and BAO data, so the lambda Godard matter model. But this is not that easy, okay? Because if we want just to put in agreement CMB and the Hubble constant, that's easy. The point is that we want also to be in agreement with BAO and supernovae data, and their combination is giving this line of degeneracy here. So if we want to be in agreement with a higher value for the Hubble constant, we need a lower value for the sound horizon. If we want to be in agreement with a lower value for the Hubble constant, we need a higher value for the sound horizon. So for this reason, we are dividing usually the solutions in early solutions and late time solutions. The late time solutions can increase the value of the Hubble constant because they decrease the expansion history in the intermediate redshift, but you move only along this line of correlation because your sound horizon is fixed at recombination, so you cannot change it. So every time you have a late time solution, you move here, and you cannot ever be in agreement with BAO and supernovae. While an early time solution, like for example early dark energy or neutrino effective number, can move along the right direction of correlation, so lower the sound horizon at the same time increasing the value of the Hubble constant, but unfortunately their mean value is always around the lambda quadrant. So at the end what we see is a volume effect, so the constraints are larger because you are increasing the number of parameters, but in order to be in agreement with shoes we need to add a prior on H0 dragging the value of the Hubble constant towards the local measurements. So what we need is really an independent measurement of the sound horizon, and we forecasted the possibility of doing that using luminosity distance from a gravitational wave standard sirens of LISA, combined with angular diameter distance of BAO from the legacy of DESI, for example. In this way, you'll be able to reach a precision on the sound horizon of 1.5% and distinguish between early time solution and late time solution with a significance of 4 sigma. So now I will spend the last few minutes to contradict what I said, because I said that not the late time solution don't work, but that's not really true. The point is that they don't work if we have standard dark energy. If we have something that we call the omnipotent dark energy, that is a dark energy can do everything, can have a phantom crossing, be quintessence, phantom, have a negative dark energy density, a positive dark energy density, be non-monotonic, have oscillations, have a singularity, and have all of them at least one point of the parameter space. And this seems difficult to do, but actually it's very easy. We can tailor expand the dark energy density around the possible extrema. So this will be the expansion rate and the equation of state of the dark energy. And these are the dark energy equation of state, how they behave. As you can see, this cannot be recasted in CPL parameterization just because, for example, there are 2 phantom crossing here. So this kind of solution work very well. So can solve the Hubble tension if we have a phantom crossing of more than 2 sigma, because we have the dark energy that is non-monotonic and can be negative, and also fit the oldest DSS BAO data much better than lambda quadrant. It still works with the new DESI data, but unfortunately it doesn't work with the supernovae data at all. So this is something that still don't work. Another model, a late time that works very well, is a model of the interaction between dark matter and dark energy. In this case, we can consider this interaction rate proportional to the dark energy density, and the conformal Hubble rate via the dimensionless parameter Xc that is quantifying the strength of the coupling. So if we have a model like that, since we have a flux of energy between dark matter to dark energy, we have less dark matter in the universe. And from the CMB, we are measuring accurately well omega mh squared. So we have less dark matter, we have natural Nyquist value for the Hubble constant. And this is why we solve the Hubble tension not because of a volume effect, but because of a stronger overlap. And you have only an upper limit for the cold dark matter density. So adding a prior on H0, we have more than 5 sigma indication for a coupling different from 0. But can we believe to this result? Actually, no, because what I said before, okay, there are correlations between the parameters that can change your results. So if we consider a fiducial model with no interaction between dark matter and dark energy, and then we simulate an experiment like Planck or BAO, if we then analyze this mock data set, letting the interaction between dark matter and dark energy free to vary, we have 3 sigma detection for an interaction that is not in the fiducial model. And in order to be able to have only a lower limit, we need to break the correlation, and this is possible if we use BAO data on top of your Planck data. And again, these are mock data. So now what happens if we use the real BAO data with the real Planck data? So we are only 1 sigma for a coupling, so it's not significant. The Hubble constant still goes up. This is for SDSS, but the Hubble tension is at the level of 2.1, 2.6 sigma, so it's not 7.1, but it's still something in that regime that I don't like that much, okay, because you don't understand this statistical fluctuation or a residual tension. The point is that this is instead working very much better with the DESI BAO data, so we can solve the Hubble tension at 1.3 sigma with an interaction at more than 2 sigma. And if we consider a Bayesian comparison with lambda quadrant matter, this is as good as lambda quadrant matter, but we can solve the Hubble tension at the same time. Okay, now the trick was to have something that is proportional to dark energy If we consider other models of the interacting dark energy, like for example something that is motivated by trace-free Einstein gravity, where Q can be seen as an effective cosmological constant. In this case, is, the energy momentum exchange is proportional to the dark matter density. This kind of models still work well with the data, still have some kind of indication for a coupling different from zero, but cannot solve the Hubble tension anymore. So I will skip this because we said I should finish by time. Okay. So this is my summary. Lambda quadrant matter still fits impressively well each data set separately, but it fails when it wants to fit them all together. At the end, the lambda quadrant matter is a model based on completely unknown ingredients, dark matter, dark energy, and inflation, that lack any fundamental explanation or direct detection. So they work phenomenologically, we cannot understand them, and now we have problems in the standard models. This is what I call cracks. There are 7 sigma tension for the Hubble constant. There are problems in the CMB, lensing anomaly, curvature, low optical depth, possible negative neutrino mass, hints for dynamical dark energy. So why does it matter? Because cosmology now is able to probe physics beyond the reach of laboratory. But if these tensions are due to systematics or a wrong assumption about the model, then any interpretation must wait. So physical precision cosmology is only meaningful if data are internally consistent and trustworthy. When I started my PhD, people were saying, we can do precision cosmology. I don't think we can do it anymore, how the data are now. So I think we should reevaluate our assumptions and method before claiming to be able to measure the universe at percent level accuracy. So thank you so much.
Questions, we'll start at the front.
Yeah, you mentioned that in some models for the evolution of the dark energy equation of state, you had like a double phantom crossing, and that at present it could even be phantom. Is that right? Will you comment more on that?
So, I
think this was early in your talk.
These ones?
I think it was early on.
I think you're referring to this one, maybe.
Well, you had some models which had like the wiggles in the W against the...
Okay, like the oscillations, you mean?
Yeah.
But we have
right,
only phantom crossing, actually,
so
okay? This is the phantom crossing here.
Right.
And this is quintessence today. So it goes, like, oscillates, is quintessence today.
Sorry,
so it's like CPL, but on top of CPL, there are these oscillations, and this fit better the data than CPL.
Have you worked out like the...
We are doing now the reconstruction very precisely with the same force author Daniel that is sitting there, and there will be something nice to see.
But these give a higher base in evidence than lambda CDM.
No, this is favored over CPL. Oh, sorry, lambda CDM. Yes, but because we have one more parameter.
So it works better than lambda CDM?
It works better than everything. Better than lambda quadrant matter, better than CPL.
Even though it's more flexible?
Yes.
Okay.
So just to be sure, here you are just assuming the dark energy
Equation.
dynamical, but there is no interaction.
No. It's just, okay. Yeah, we tested a bunch of models, okay, that are dynamics, with different dynamics, okay, and that more or less mimic a CPL model because we want them to be phantom in the past. Pivot scale.
Where a certain redshift W is -1.
I mean, this is variable, okay? The phantom crossing can be wherever. So this is variable enough to be able to have whatever.
So you always find the phantom crossing?
But they always find the phantom crossing. Yes, the evidence for phantom crossing is much bigger than the evidence for dynamical dark energy in the data.
That means you have a very precise scale factor A for the
This is what, yes, this is what I was showing here, you see? Right. So the fact that this is very much strongly elongating along one of these lines is giving you an evidence for phantom crossing that is stronger than dynamical dark energy itself. Yes.
Have you got any ideas why dark matter congregates with matter?
I didn't understand. What is your question? Can you repeat?
Yeah. Do you have any insights into what causes dark energy and dark matter? And what do you why do you think dark matter congregates around matter in the universe?
I mean, I think if I had this idea, I would win the Nobel, right? Because I would explain.
From a practical perspective.
Okay, so if I have to be very, very sure, very, very honest with you, I'm not that sure that there is dark energy, dark matter in the universe, right? Because I think the point of my talk is that we really don't understand what is going on. So at the moment, we have some sort of prescriptions that are these prescriptions here. These are the ingredients we need, okay? Then we call them dark matter and dark energy because we want them to have this precise characteristic. And then in the lambda quadrant matter, we are choosing these. Okay? But if you can do the same dynamics, the same thing with something different, for me, it's perfectly fine.
Yeah.
Hi.
Hello.
Two comments. One is in reply to the gentleman there. The requirement of dark matter is not
Please speak up.
The requirement of dark matter is not only coming from the dynamics of the universe at large. It is also corroborated by many other independent observations, like rotation curves of the bullet cluster. So, in a sense, this is not really a mystery. I mean, it's either a heavy particle, a WIMP, or a primordial black hole. Cosmologically, they behave the same way. Dark energy is a different animal. It may not exist, as you say. They may be completely different. I actually wanted to ask a different question. There was a recent paper from Savas Nesseris, I don't know, you probably know about it, where basically they extend the CPL parameterization and they consider higher orders because CPL parameterization is really a Taylor expansion, even though Lindbergh disagreed.
Yes.
And so they consider W naught plus WA 1 minus A plus WB 1 minus A squared plus WQC 1 minus A cubed. And they find that there is no Hubble crossing. I thought this was a neat idea. What do you think?
I mean, what I remember about the paper is that they are, I mean, if you increase the volume of the parameter space, right, you lose constraining power on something. Okay, so I think that's why they don't have phantom crossing in that case. I mean, is a Taylor expansion? Yes, but I mean, the point is that, okay, you need something that is, to have a phantom crossing, is like you hang around this line of correlation, right? So if you are increasing, if you are expanding this volume, like if these constraints are expanded, then you lose completely the indication for a phantom crossing. But I need to look at the paper better.
Do they get higher Bayesian evidence adding more Taylor series?
I think they say that you have like, you don't need 3, no, I don't remember, but there was a conclusion that going beyond a certain kind of, yeah, exactly, going beyond a certain kind of expansion is not useful anymore, but yeah.
What is your opinion on this idea that if we live in a void or in an overdensity, it could have an impact on the measurement of the Hubble constants? So do you think this is really a too small effect?
I think Indranil is going to talk about that probably, right? A couple of days. Yes. Yeah, I mean, this is one of the ideas, right? There have been proposed many, many, many ideas. This is one of them. Unfortunately, we are not at the point where we can choose one over the other yet. So yeah, we will see.
And on that note, that's a good point, I think, at which to thank our speaker again.
Thank you.
is our very own local Alexia Lopez.
Say that again.
Don't forget the news.
Thank you.
Don't forget the mute button. He's going to be talking about ultra-large scale structures.
Hi everyone, thank you all for coming to start with. Obviously I really wanted to organise this meeting to gather a bunch of cosmologists with the same ideas of wondering about the universe on its largest scales from observations and theory. So I'm an observationalist, so I'm going to show you some data. This work has just been submitted in the archive last night, so it should hopefully be on the archive maybe tomorrow to read. So this is a giant ring on the sky. It's the third kind of structure of this type. If you've been following, there was the giant arc to start with and then the big ring. Oh wait, I clicked this one, don't I? Do I? Let me just... Oh, there we go. I was just because I wasn't clicked on the screen. So I won't go into the whole why are we studying large-scale structure for cosmology, because we're all here for the same reason. But as an observationalist, the data is really important. We do need to test the cosmological principle, the foundations of our lambda CDM model. We need to understand about the evolution and growth of large-scale structure and formation, and ultimately all of this to understand our current standard model. So my talk is laid out like this. I briefly go into the first three here, the method, a quick recap on the giant arc, and a quick recap on the big ring, and spend the majority of my talk on the current work. So apologies if I do speed run the first few slides. This is the method. I'm just going to quickly fix... No, never mind. I'm not going to fix that. I'm going to leave that. Sorry for those on YouTube, that is cutting off the top of the presentation, but never mind. So this is the method. 4 steps I've put it into. The first step is a schematic demonstrating the method. We have really bright background quasars, bright background sources in the distant universe, and as their light travels across the universe, it passes through low ionized gas, which traces galaxies and galaxy clusters. We look at, in particular, magnesium-2 absorption, which is shown in the third panel here. It's a very specific doublet feature in the spectra. Number 2, we have 750,000 quasars covering 1/3 of the northern sky. So this is our data, our first order data. So these are all the quasars. You can see that there's lots of inhomogeneities, which is just survey biased mostly, but there are also intrinsic inhomogeneities in that. Then independent authors apply their own pipeline to each individual quasar to measure for this magnesium-2 absorption doublet, and that is what's being used to indicate the presence of galaxies and galaxy clusters. So as always, the wavelength here is the redshift, and the position on the sky is given by the position of the quasar. And then lastly, we plot the data in these 2D images. These 2D images are a 3D slice of sky. The grey smudges, or the grey contours, are showing you the matter distribution of the galaxies and galaxy clusters. And the tiny little dots in the background, these are all the quasars in the background of that. So that's the method. Where's my mouse? Okay, so a giant arc, a quick recap. The giant arc was discovered serendipitously. It's this huge arc of magnesium-2 absorbers spanning roughly 1 gigaparsec scale to the present epoch, and it's at a redshift of about 0.8. This was actually discovered in some of the older data that we used to use back in the day. We did apply a lot of different statistical and observational assessments. I've here just shown 2 out of the paper, but there was a lot more analysis that we did here. But this is just a selection because I'm just giving you a quick recap. So one of them was the single linkage hierarchical clustering algorithm, or Friends of Friends, or MST. It connects the points and identifies candidate structures. And we assess these structures statistically with the method of convex Hull of member spheres. And this identified a 4.5 sigma for just the black dots here. So here, this was the visually identified giant arc, but it was split by the SLHC, or the MST algorithm, which is to be expected in this kind of data because we don't have a continuous background. We have quasars, which are responsible for our detection of the magnesium-2 data points. And we also did a more powerful field analysis using the 2D power spectrum analysis, and this identified significant clustering corresponding to characteristic scales of about 270 megaparsec, which we reasoned was probably the thickness of the giant arc along here. That was probably what that was detecting. A big ring on the sky, again, similarly, we had a lot of different observational and statistical techniques, but these are just a couple. So the big ring, again, was identified visually to start with because it was visually obvious in the field. When we switched our data from the old DR7, DR12 to the newer DR16, and we looked at the giant arc, there was this visually obvious ring of magnesium-2 absorbers to the north of the giant arc. And again, in the same redshift, in the same cosmological neighborhood at 0.802, which begs the question, is this a special redshift? I don't know in particular why this particular redshift, but moving on. 2 ultra-large scale structures now in the same redshift. Again, we used the SLHC algorithm, which splits this structure into multiple candidate structures. So we this time used the convex Hull of member spheres to assess 4 different estimates of the big ring. The big ring that was identified with MST, the big ring that was identified by the fill finder on the right here, and 2 versions of the visually identified big ring. So we were trying to assess lots of different versions of the big ring estimate, giving a 3.7 sigma mean here. And then, yes, this newer test that we applied was the objective 2D filament identification algorithm, fill finder. So this objectively identifies where the filaments are in a 2D pixel image. So where are we at this point? We have these 2 ultra-large, large-scale structures in the same cosmological neighborhood, separated by only 12 degrees on the sky. When we did look at the data, we noticed this, and I hope you can see this with my pointer, this interesting northern filament. And it almost looked like it could be an extension of the giant arc. So the first 2 times I've mentioned the giant arc and the big ring, I've said they were discovered serendipitously, or they were discovered because they were visually obvious. In this scenario, we've now predicted a giant ring because of the indication of a little northern filament above the big ring and starting to follow the pattern that we might be seeing here. Are these features common? So we made a prediction that maybe with enhanced data or better data, that we might see a giant ring feature that would envelop the big ring. So this is the giant ring feature here. I'm used to looking at this data, and sometimes I fear that when I show this data to people, they go, what am I looking at? So I'm going to highlight for you here. It's this thin northern filament here, which goes down here. And then there's this messier, ambiguous southern region, which contains the giant arc. And again, it comes up here and then joins back up. So this is the visually obvious giant ring feature in the data. So at this point, the predicted size of the giant ring is massive. So the signal is reduced in the data. We experiment with trying to increase the signal with making signal-to-noise selections to try and decrease the noise in the data. And also, given the size of the giant ring, we're now expecting to look in a much wider redshift slice. But we are limited by the data. If we try to extend the redshift slice too much, we chop off the background quasars that allow us to even see this image. So we extended the redshift slice just on the near side instead to identify this this image. The other thing that we did was this project plane method, which essentially just allows you to project the points onto different angles so you can tilt the field, and it slightly changes the perception of what you're seeing in that field, because usually we just look at 2D along the line of sight. So we then also, again, just for a visual demonstration here, used a 2D nearest neighbours method, which joins the 2D nearest neighbour pairs. And in the right-hand side figure here, it removes entirely the points which do not have a nearest neighbour. And this was, the idea of this was to try and reduce noise. The biggest problem of this new data of this giant ring is that there is more noise because it is such a big field with such limited data. So when we apply the 2D nearest neighbours method, we emphasize these void regions in between the giant ring and the big ring. So we can still see the big ring here, but we get these really big empty void regions here separating the big ring and the giant ring. So we again apply the fill finder. So this objectively identifies the filaments in the field, and the filaments that are identified agree with what we visually identified. You have the clustered region at the bottom, you have filamentary singular filaments coming up the east and the north region. And then this left-hand side, this is important because I talk about this more in the paper, but a little bit in this talk as well, is this branching. We have a left-hand side branch here and a right-hand side branch here. I must note that these are the tangent plane images, not the project plane images that I was talking about before. So there is a little bit of change between these images, but the line of sight and the projection are quite close. So we can generally correspond which absorbers are belonging to what. Anyways, so we have this inner filament and this outer filament. We call this the branching in the left-hand side. With the fill finder, we increase the size threshold to identify what the largest filaments are. So this is the largest whole filament in the field, which is the part that corresponds here. It's the lower east, southeast of the giant ring. So when we plotted these identified points from the fill finder with the original giant arc members, we do get this impression of the giant arc extending into the giant ring. So this is when we were talking about the support of the giant arc is extending into a giant ring based on this trajectory. So giant ring analogues, can we make them in random data? So something that I emphasize a lot and something that I do think maybe gets missed a little bit or underappreciated is the visual obviousness of the structures that we're looking at. So often when you're not going to ultra large scale structures or large scale structures, but say we're just looking at superclusters, and more often than not, these things are just visually obvious, and there's no general qualms about this. So when we get to ultra-large scale structures or large-scale structures, it's the same thing. We're seeing these things because they're visually obvious. So when I look in random data, which is the left-hand side, these three cuboids here, I don't think, when you can judge for yourself, but in this data, I don't think it looks like the real data. I don't think there are rings and arcs and really dense clumps. This is just random Poisson data, and it looks random. On the contrary, if you just, this is a really hypothetical, just an experimentation, but if you just add a few random clusters, so these two boxes side by side, they have the same field density, they have the same number of points, but in this one there's just a few added dense clusters, and you just get a little bit more ring-like, clumpy, arc-shaped features in this cuboid data. This is just an experimentation to say perhaps the real data looks more like this, which might be indicating that maybe the real data is not just random Poisson. That's the argument there, really. So the statistics of it. We define an elliptical shell based on the ellipse parameters of the giant ring prediction. So this is the ellipse parameters of the originally predicted giant ring that only was predicted based on a giant arc and a little northern filament. But this entire precise, well-defined thickness elliptical shell had a 3.38 sigma significance, which I think is remarkable considering it was just a prediction based on only a giant arc and a thin northern filament. And no, I'm just mentioning whether or not we're in the tilted field or the non-tilted field. I haven't really gone into that, but we can talk about it later if you want. I mentioned earlier about this branching in the left-hand side of the giant ring field. So the left-hand side branch of the giant ring does seem more closely aligned with what was originally predicted from the giant ring. So the giant ring prediction seems to go through the absorbers that are more related to the left-hand side branching from Fill Finder. The inner or the right-hand side of the branching from Fill Finder appears more associated with what we then visually identified as the giant ring. So we're getting these two different versions of ellipses. So I've just highlighted in pink here what was visually identified, but also what was corresponding to the inner filament of the Fill Finder identification. So all I did to avoid changing too many parameters, I just moved the ellipse over and I reduced the semi-major axis. I didn't change the tilt or anything like that. And then this calculates a 4.04 sigma significance. And this is just against 1 million random fields. It's a very rudimentary statistical test. But we can then apply an ellipse matching method which optimizes the ellipse signals. So this table here is just telling you, we step through, x positions from -10 to 140, and y positions, semi-major axis, semi-minor axis, and ellipse orientations. So we have 4 ellipses in this field. We have 2 which go through the left-hand branch. The orange here is the original giant ring prediction, and the green is the optimized ellipse. So these two are very close to each other, but there is a gap here towards the bottom. The ellipse prediction goes much higher than the optimized ellipse. We then have a second set of 2 ellipses here which go through the inner branch of the giant ring. This was what we visually identified as the giant ring and was the second optimal elliptical shell in the field. So these were 4.73 and 4.47. Now, bearing in mind that I hope I have emphasized, that this was a prediction and then what was also visually obvious. We also apply the 2D power spectrum analysis to the giant ring field, and this identified, these 6 points over here, is identifying significant clustering on characteristic scales of about 320 megaparsec. We say, is this characteristic scale of not voids? Is there a general separation between the areas which are not voids of about 320 megaparsec? maybe it's indicating something like this when we correspond with the giant ring image itself. All right, well, what about random data? Let's think about this ellipse matching method. We now have tested around 370,000 elliptical shell trials. That's quite a massive look elsewhere effect, and it's a really favoured term in cosmology, the look elsewhere effect. So yeah, you can apply this same method to random data, and you do find statistically significant ellipses. So does this mean the ellipses are real structure, or does this mean that real structure is just noise? Have we refuted all large-scale structures now? Probably not, because this is just an effect of the look elsewhere effect, something that does get undermined a little bit. So you can apply single candidate structure assessments to random data and do it a million times, and you will find statistically significant results. But are they real structure? Are they visually obvious between these two fields? Can you see that? And more importantly, applying a second statistical test shows that random data is entirely consistent with random data. Absolutely remarkable finding, perhaps. Sorry, I'm being a little bit too sarcastic here. The giant ring, it's a visually obvious and statistically significant result in a statistically significant field, something that appears anomalous compared to random data. And also, we applied the 2D power spectrum analysis to samples of flamingo 10K data. So not just looking at random Poisson, but looking at cosmologically simulated data, which was also found to be entirely consistent with random data. So we're getting these results that the real data is not like random, and it's not like what we simulate in these big simulations like Flamingo 10K. So this is something I think should be focused on. It's important. You can't just take one statistical test, bung it on some data and say, oh, well, everything's just noise and nothing is interesting anymore. So yes, the giant ring was predicted, and even the prediction was found to be significant, and then we later optimized that with a systematic approach. There do appear to be these two different versions of the giant ring, which we indicate might be overlapping separate ring features, but this will require a lot of different work. So yeah, much more analysis is needed, but the initial observations so far indicate that the giant ring field is indeed quite interesting and curious for cosmology. So I think I've just gone over by a couple of minutes. I will take questions, but also this leads on nicely to Sir Roger Penrose's talk, which will be after mine, on the interpretations of my results with his model, conformal cyclic cosmology. Okay, thank you.
Thank you, Alexia. Unless there are any further burning questions, okay, I was going to suggest we roll straight on and take more at the end. Go ahead, Joe.
Okay, so this is intriguing. If the giant rings were to be traces of the gravity potential to any extent, then you would expect correlations with the CMB because of the
now can you save that
integrated sex orbit thing.
Can we save that one for after Sir Roger's talk?
It's nothing to do with his talk, actually.
Well, funnily, it does a little bit, because his original observables for his model were actually looking in the CMB. And there are a couple of papers that talk about finding ring features in the CMB with temperature differentials. So I do think this might be relevant.
The point is, you know where to look now.
Yeah, it's a good point, actually. I do need to look at the positions of those rings and also those Hawking points as well, which I think are little points in But yeah, I could do that next.
Just a quick question. Does the giant ring and the giant arc rotate around a common point?
Rotation would require a lot more data. So I don't think I can measure the velocity in these magnesium-2 absorbers, especially not with the resolution I have. So I could not say whether or not there was some kind of rotation or something like this.
There was something at the centre which was sort of attracting the two features.
There was a point. I mean, of course, with the big ring, there was obviously the question of, is there something in the centre? I didn't find anything obvious, but I'm sure there was, or maybe that person isn't here today.
Last one.
Thanks for the talk. So it's not clear to me how you assign a redshift to which element of the ring. And the second question is, surely this structure
sorry.
Surely this structure should be visible in some other observer rather than this magnet.
So, real quick, the redshift is each magnesium-2 absorber, when it's measured in the spectrum, it has a wavelength corresponding to that, and then that's the redshift. The second question is a really good question. We've thought about it before, and given the precision of the redshift measurements of the magnesium-2 absorbers, we thought that maybe that could be part of the reason why you see more features in the magnesium-2 versus other data sources. However, we do also cross-correlate sometimes with other data, and we find general agreement between them, but not with the same level of detail. So I'm going to cut that answer short, but I'm going to get Roger set up. Thank you. This might take a little minute, so if you want to go grab more cookies and tea, etc.
Hello, hi. We don't. That sound is absolutely great. Hello, hi. We don't. Hello?
On.
Can you hear us? We had two microphones on.
Oh, is that it?
I think it's okay now.
Oh.
Uh,
Is anybody hearing anybody?
can you see the presentation now? Can anyone hear me?
I hear you very well, Helen, and we can see the slides too.
Good, but I don't know where anyone else is and whether...
I think Alexia said they do not have permission to share the screen, but they hear you too. You can start.
Okay, Roger, you can start.
I can start. No.
Yes. Now, these are you go...
Oh, wait a minute.
These ones. This one.
Just
that one.
Just this one?
Yep. Unless you want to go back and then you use that one.
Oh, it's the arrow, okay.
Yeah, but yeah.
So you can see the title now, but I don't... Will I get any back from anybody else? No. I just talk?
Yes.
All right. Well, this is the title you can see. Conformal cyclic cosmology and Lopez giant rings. Well, I can say rings in the plural now because he certainly sees two, as far as I can make out. I'm very impressed by all that. I'm going to say only things which are blatantly obvious, in my view, rather than the subtleties that we've been hearing about. So let me try and find the first slide. I just pressed that button. Now, this is a picture of what we think the universe is like. Of course, I have to throw away a couple of dimensions, but the time is going up the picture, and you see the Big Bang at the bottom, and expansion, and then slowing down a bit, and then the expansion, the exponential expansion that we see at the end. Right at the beginning, the normal claim is that there should be an exponential, well, inflation, you see, there's a little arrow pointing at inflation. You wouldn't see it in this picture anyway. I don't happen to believe it, but if you don't believe it, you have to believe in something else, and something else is what I'm going to try and talk about. As I say, I'm only talking about blatantly obvious things. And one of these things is that the time, or the equations of general relativity and the primary equations of detailed physics, apart from the statistical ones like the second law, well, that is relative to all this too, relevant to all this. But that means you could have a reverse picture with the universe collapsing, and that would be a perfectly consistent sort of picture if the other one is. The only trouble is that if we have anything like our universe with black holes and all sorts of stuff going on, it's much more like that. That is to say, it's highly irregular, singularities being extremely complicated, probably like the Belinsky-Lifshitz-Kalatnikov picture, where you have extraordinarily complicated behavior, with things oscillating in different ways and exchanging the oscillations with each other and all that sort of stuff. But nothing like what we see in the Big Bang. So the Big Bang is not like that. It's, well, yeah, I'll go back, I think. This is exactly what it's not like. We don't see incredible complications. It's not like the reverse of immensely congealing black holes and things like that you could expect to see in a collapsing universe with this horrible behavior, maybe Lifshitz, Kalatnikov kind of behavior, which would be a horrible mess. We see something much more smooth and simple. And people seem to say it's got something to do with the inflationary field. I always puzzle about that because the inflationary field is, well, you've got the inflaton field, it's a symmetrical in time equation. And I can't see why this explains why the universe is not like this. Certainly not like this. So we need a different explanation in my view. So let me continue. And I want to talk about, first of all, the main types of curvature. There's the Weyl curvature. I'm imagining you have, say, some light rays which meet at a point at the top. And these light rays, as they go back, you might be looking at something. And the distortion you would see would be in the Weyl curvature. That's the Ricci curvature. Well, there's also the trace of the Ricci curvature, which doesn't affect the light rays at all, so you don't see that part. But the trace-free part is just like an ordinary lens, which could be magnifying. It is like a magnifying lens, in fact, and you don't have any directional features. Whereas the Weyl curvature is like a purely astigmatic lens, and you get these distortion effects. So I want to separate out those types of curvature. That will be important in what I want to say. What's that picture doing there? Goodness, that shouldn't be there. I'm not quite sure what's happened. Is this the right slide?
You've just gone too far forward.
Oh, I see. Oh, so that's what I always do. Sorry.
Oh, don't know what's happened.
Oh, it's probably got into the. That's it.
That's it.
That's not it, actually. But
Do you want to go back or forwards?
But this is backward, isn't it? There's no backward. Sorry.
You deleted the slides as you've gone. I don't know.
No, that's not the right slide. What's happened? Is it the right show they've got? No, that's the end. Back. It's disappeared. I don't think this is the right slide. That's not the right show. No, those shouldn't be in there. Those are probably the ones I pushed to the end, and then not there. Let's have to go back to the beginning.
There we are.
That is the beginning. Yes, that looks more like it. Yes. I am quite likely to press the wrong button.
Yeah.
Oh, no, that isn't the wrong button.
You've just, Roger.
What?
Sorry. Don't touch for a minute. It is the right one. It's just.
But that's
you
not
keep.
the slide, yes.
Yeah, you keep. But by pressing both of those, you're going to the end all the time. So, where do you want to be?
I want the next slide.
Okay, those aren't working. I will.
Perhaps I can just slide it down like that. Will that work?
Yeah, which slide are you on?
Not further up.
This.
Yes, that'll do. That's
this one. Okay.
Yes.
Oh wait. Right. Okay.
Sorry about that.
So yes, sorry. There we are.
No, it's this button. Is that
Yes,
the right button?
yes, but you mustn't press any of the others.
No, I'm very likely to press the wrong button. That's one of my faults. Okay, that is like what a collapsing universe would be like, collapsing to a horrible mess. This is not like what we actually see. We look like something completely different. So I'm not talking about subtleties, I'm talking about the blatantly obvious. So this is the Weyl curvature and the trace-free Ritchie curvature, which I mentioned before. So what we seem to see in space-time singularities in the future, that is to say in black holes and whether they congeal with each other or what, the Weyl curvature goes completely wild, goes to infinity, not just straight to infinity, it oscillates in incredibly complicated ways. Whereas at the Big Bang, the Weyl curvature seems to be zero, very small anyway. And we have to explain that. We have to understand this extraordinarily, not a subtlety, it's just blatant. So let me go on. And I'm going to talk about space-time geometry. Now, the metric of space-time geometry, well, I say is 10 components to find the metric at any point. And these 10 components, 9 of them, in effect, are where the light cone is. The light cone can be pointed right upside down or in some way. But this light, or I should call it I can't even remember that. the null cone. Yes. The null cone is, roughly speaking, 9 out of the 10 components. More correctly, it's the 9 independent ratios of those 10 components. So the one thing we don't have with the null cone is the scale. And the scale is determined by, well, the two most famous formulae of 20th century physics. That is Einstein's E equals mc squared, and even earlier we have Max Planck's E equals h nu, where nu is a frequency. And the two of them put together tells you that energy is a frequency. So that if you have a frequency defined, that is really, I imagine these little hyperbolic surfaces sitting inside the light cone, giving you different distances from the origin point in the middle. And when I say distances, it's really times. And the crowding of them is the frequency, and that is the one more component we need to get the metric. I'm putting it this way because the thing which determines the metric is really of a different character from the null cone structure. The null cone structure by itself is the conformal structure. And a lot of what I want to talk about will be conformal geometry. And the Dutch artist M.C. Escher has these very beautiful figures which he calls circle limits. This is actually his first one, but in some respects it's the best one to use because you can see these fish creatures have eyes which are circles, and those little circles remain circles as you go right up to the edge. And I've actually seen the original picture here, and then incredibly accurate, right up close to the edge. So this says that there's no distortion in the picture. That is to say, the little fish creatures, at least their eyes at least, are the same shape when you get to the edge. What's different is the size. So you can play with the scale up and down as long as you make the shapes, small shapes, are preserved. And that's the conformal structure. And so when I talk about conformal geometry, that's what I mean. You can stretch out equally in all directions, or you squash them down. And the advantage of this, for me at least, is that you can represent infinity. If infinity is nice, you can represent it in a picture like this, where you have a boundary. And in space-time, of course, the boundary would be three-dimensional. Space-time is four-dimensional, and that three-dimensional boundary could represent infinity. Okay, let me move on and make sure I press the right button. Okay, so what you can do is you can squash down infinity, or you can stretch out the Big Bang. And that's the sort of picture I've done here. it may look as though that's like a cylinder on the right. It's not really a cylinder, because if you look carefully at the back, you see it sort of wiggles around. I've only drawn it that way because the curvature might be negative, and it's rather hard to represent that. So I'm just imagining it could do what it likes at the back, and it may go off to infinity in a spatial direction as well. But the main point is what you see locally in the space. And so I draw it as an almost cylinder, which can keep on going at the back if you like. But that represents the space. So it could be, doesn't have to be closed up, is what I'm trying to say. Doesn't imply that the spatial geometry is closed. It's very likely not. Okay. Now, what you can do then is squash down infinity, which is what Escher does, or you can do the opposite and stretch out the Big Bang. And the thing about the Big Bang is it seems to be of the character that if you stretch it out, you get something reasonably smooth. It was my former student, Paul Todd, who really looked at this rather carefully and examined possible perturbations of the Big Bang, and there could be structure in there, but on the whole, it seems pretty well something which you could uniformly stretch out and have a reasonably smooth, stretched out Big Bang. So the squashed down infinity and the stretched out Big Bang are both reasonably sort of smooth. And the idea here is that you take that a bit more seriously, and you say, why is the Big Bang so smooth? Well, because it was the remote future of somebody else, or some other universe, if you like, or some other eon, I'm calling it. So you have the universe is one of the, what we normally think of as the universe is, say, the middle one. And the middle one would be a picture that I showed you before. But the Big Bang, when stretched out, is really smooth because it's the squashed down infinity of the remote future of the previous one. And then this can continue indefinitely in the temporal direction all the way up. Now, what's I going to say here? It's not exactly, sorry. Was there a comment? Sorry. Yes. Now the point, why can I get away with it? You see, because the conformal geometry is there, but I've lost the metric, the scale. Now the places where you can lose the scale is where you don't have any mass in effect. And in the remote future, the idea is, well, the original idea is you just had photons. It's more subtle than that. But let's think about just photons. Photons have no mass, and therefore they don't determine the scale. Big and small is the same. Maxwell's equations are conformally invariant, and so that's a place where you lose the sense of scale. There would be other particles around, not just photons. Very possibly just things like electrons, maybe some, well, neutrinos and electrons and positrons, maybe protons, or maybe the protons decay. The idea here is that there is an effect, which means that the electron mass does fade away in the remote future. One can put an argument for that, especially when you have a negative cosmological constant in this case. I don't want to go into that argument particularly here, but there is an argument which you can make which suggests that maybe the mass does fade out in the remote future. It has to do with the Casimir operators which you have when you have a de Sitter space rather than the Minkowski space. But let's not go into that. What about the Big Bang? Why can you forget about mass there, or scale, you see? Well, you can forget about it there because the energy is so enormously large that when these particles are moving around at great speed, that in fact the energy in the particles is, or say the mass, is entirely kinetic. There may be a mass to the particles, but it doesn't make any difference because the actual motion around is what dominates. And in the limit, when you get to the Big Bang, the mass of the particles is completely irrelevant. And so the two places where you lose mass are in the Big Bang and in the remote future. So when you've lost mass, that means you lose scale, and therefore it's not so stupid to join on the remote future of one eon to the Big Bang of the next one. You could say, what could be more different? One very cold and non-dense, and the other being very dense and hot. But you see, in the limit, hot and dense and disappears in a way because of the temperature being so high. And this means that you don't really see the mass term in the particles. The mass term gets irrelevant. The hotter they get, the kinetic part dominates the energy in the particles. So that's the excuse that I have for joining them together. All right, it's all very well to have an excuse, but you have a reason. Well, the reason is that in this picture, you do lose all the Weyl curvature because it's all, well, there's a good argument about that. Does it all disappear in the remote future? Certainly, superficially, it largely disappears. Let me press the right button here. In fact, signals can get through. This is one important point. I should say that there are two effects of CCC which have been confirmed in observation. So it's not just an idea hanging around. The first one was the fact that the CMB seems to have rings of slightly enhanced temperature. So this is a tiny effect, you might say, but it does seem to be significant, not to a huge degree. Let me take, I did an analysis with Vahe Gerzajan, my Armenian colleague, but neither of us was any good at doing statistics. So we looked for rings in a different way. And the way we look for rings, we're saying we twist the sky and see whether the number of these rings is reduced when we twist the sky, because then you're looking for ellipses rather than the circles, and the ellipse density just drops dramatically. The more you make them look elliptically, the fewer you see. So this was our reason for saying these rings are real. The Polish people, headed by Krzysztof Meissner and Paweł Nowrocki, and a couple of other Poles that were involved, but they looked at a different form of analysis. They knew how to do the statistics, and they came up with a confidence level, not a huge confidence level, but it was about 99.5% on two different satellites. One was the Planck satellite and the other the WMAP satellite. And more than that, they found very specific points in the sky, which are the centers of rings, which seem to have some significance, not a huge significance level. But one thing that's rather remarkable is that the 5 strongest points looked at the WMAP data were in exactly the same places as the 5 strongest points in the Planck data. I don't know how the statistics gets affected by that, but it seems this is a pretty strong piece of evidence that there is something there. The other effect that we found was something quite different. These are things called Hawking points, where what happens in the very remote future? Well, most of the sky, most of the space-time is getting emptier and emptier and emptier. But there are certain places where you get what happens to a galactic cluster. I'm talking about galactic clusters, not, say, superclusters, which may be dispersed, but galactic clusters are supposed to remain bound as the universe expands. And so these clusters more or less remain together, and you get, as the stars get older and run into each other and all that sort of stuff, they produce black holes. And you produce very large black holes, and these black holes will swallow stars, swallow each other, and that will be one of the main features of these things. Now, what will happen to those black holes in the remote future? Well, you have to wait an awful long time. Depends on how big the black holes are. But the idea would be that Hawking evaporation takes place and eventually they disappear. But all the radiation that comes from it, since it happens so late, something like 10 to the 100 years or more, that late that in the conformal picture, it's virtually a point in the scale. So it doesn't matter, all that radiation is concentrated in one point. It may be that Hawking radiation doesn't take place, it doesn't matter much in the picture. Could be there's just mass and black holes sitting around, those black holes sitting around forever, and they just sit around. Again, they would just look like a point. So it doesn't make much difference whether Hawking is right or not, but still I'm calling them Hawking points because maybe he's right, and I think he probably is, and that this would be a way of classifying these points. They're in completely different places from the other points because they're different phenomena. There's no reason why they should be in the same place at all. But there is a strong signal for the existence of these points. When I say a strong signal, the confidence level that Christoph worked out was a 99.98% confidence level, which I got a sort of 3 sigma or something. I'm not very good on my sigmas, but it's reasonably strong. Well, something for cosmology is a very strong signal, I would consider. So something like 99.98% confidence level that these spots are there. And they're measured by the increase of intensity as you go around them. And there is a theorem one can prove that the mass basically is conserved as you go from one side to the other. And so you can do an integral. It's a bit like an integral of electromagnetism, where you can go around a sphere surrounding it. And if you assume that the crossover is smooth, where you don't have these spots where the curvature goes infinite, but everywhere else is smooth, and then you can do an integral around the spots and work out how big they should be, and it comes out about right, apparently. So that is to say that the intensity we see of these spots is comparable with the biggest galactic clusters that we see. So it's comparable in a very rough sense, but it's plausible. Okay, well, that's the picture that I'm presenting. But also, signals can get through. I can't remember whether that was just I must be careful with pressing my buttons. Yes, this was the picture we had, and signals can get through. What kind of signals can get through? Well, maybe photons can get through, but they have to be very, very, they would mostly get scattered away in the early Big Bang. But sort of dispersed magnetic fields on a very large scale could get through. What's more significant in the story I want to tell is that gravitational waves can get through. So you can have gravitational waves getting through from one side to the other, which they barely notice the fact that the geometry's got so changed. Okay, now let me move on to the next picture. Here I just want to talk about, I'm afraid I have to use two-spinor notation, and if people are not familiar with that, well, you just have to bear with me, I'm afraid. We have at the top of the page the Dirac equation, which is split into two component spinors, and you have a pair of equations, linear equations, each one telling you that the derivative of one contracted is equal to the other one. One is primed and the other is unprimed. And if you go backwards and forwards once, you get the del operator, the box operator, and that tells you that this mu thing is basically the mass. It's the mass over h cross times the square root of 2, if I can read my writing very well there. Not much. Anyway, so it's basically the mass. That's in flat space. But still, Dirac went to consider this for higher energy spins. Well, I'm calling him his Dirac chain, is because Dirac did consider higher spinor fields, not just his own equation, but other fields of higher spin. And then you have lots more indices, but the picture is just about the same. And you lop off one index of one kind and stick another one on the other kind. And the mu again is the mass in the same relation to the other. It's the mass because if you go once one way and then back again, you find the box operator hitting the thing and giving you an eigenstate, which is the mass of the system. That only works in flat space. And I mention that particularly because in curved space, we have a very nice thing which looks like a Dirac chain. I think I've got it here. Yes, you see, I should say, this is an important point of what I want to say. What is this Dirac chain? I call it a chain because you can go on and on one direction or the other direction. Let me actually go back to say something else. I should say that this applies also to the Maxwell equations, but not very well. It applies to the Maxwell equations but mu is 0. The mass of a photon is 0. So if you try and go one way and back again, you get stuck because you've already killed it off because the mass is 0. And so you can go all the way in one direction or all the way in the other direction. And one way would give you the right-handed photon and the other way would give you the left-handed photon. That's fine. But you can't get back to where you were because you just get 0 because that's the mass. However, again, that's not quite true in curved space. And I want to continue that. Let me go to the next picture. There is a sort of Dirac chain already given to us in the Bianchi identities. And this is something I noticed fairly recently. But the Bianchi identities, when you write them in two spinors, it really is a Dirac chain. And when I say a chain, that's directly really just considered two adjacent terms of the chain, but you can go on one way or you can continue on the other way. It's all there in the paper effectively, in principle. And so you have a chain which could be as long as you like. Now let's do that for gravity. And then the Dirac chain is, let me go to my next picture. It's what I've indicated at the bottom. And you see it's 5 terms long. The one on the left is the Weyl curvature, left-handed one, and the one on the right is the right-handed Weyl curvature. And so you have the gravitons, left-handed gravitons and right-handed gravitons. And in the middle, you have the Ricci tensor. Well, the Ricci tensor is contributed to by matter, but that's trivial by comparison with the main contribution, which is the dark matter. So that is really dark matter. And I'm forgetting about ordinary matter. It's a trivial perturbation on the story here. The big story is the dark matter. And the dark matter is in the middle, I claim. That is what's represented by, well, it's the trace-free Ricci tensor. And that gives you a Dirac chain. But what happens to the mass? Because it's curved space, the mass is not the same all the way along. And it can be 0 on the outside, and it could be non-zero for the middle one. And I'm conjecturing that the term is actually something outrageous from particle physics, namely a Planck mass. Now, Planck mass is huge. And I sometimes talk to my colleagues who know about dark matter, and I say, is it possible that the mass of the dark matter particle is a Planck mass? Thinking he'd laugh at me and says, no, it's absolutely possible. And I believe that's still the case. So I claim it would be something like a Planck mass. Exactly what that is not mainly part of the story. That would be part of the real story when you work it out in detail. But I am saying that the dark matter is the middle term. The ones to the right of the middle term and to the left of the middle term are potentials for either way. This is comparable with what happens in the Maxwell equations, because you do have a chain which goes in one direction only, and the other terms are simply potentials for the Maxwell field. So they just represent potentials. So in this case, I'm saying that's what these are. The chi and the chi twiddle, the second and the fifth and the fourth term are simply potentials, both for the Weyl curvature field, which is the gravitational waves on the two outside, and the dark matter term in the middle. So that's what I'm saying dark matter is. That's the claim I'm making here. It's part of gravity. It's part of the gravity story. That's what it seems to be. It seems to react only gravitationally. So it's a sort of gravity thing. So I can consider that it well fits into this chain. And the other terms are just potentials. It does have a mass, whereas the terms on the outside have no mass. That is consistent with the picture, because in curved space, you have a correction terms to the del operator or the box operator, and it doesn't give you a mass. You have correction terms to it. So that is the picture that I have for dark matter. Now, there's another part to this picture, and that is the dark matter itself should decay. I have another picture, which is my next one, and I've only just noticed that I had it for an earlier version of the story, and that earlier version I'm claiming is wrong. I want to correct this picture, and I hadn't corrected it before noticing it was wrong. What's correct is the bottom, I claim, is that you have the dark line going into the future is a dark matter particle that will decay with a half-life of something like 10 to the 11 years. So that means that since the Big Bang, it will reduce by, well, I'm not sure exactly, maybe about a fifth of the material has disappeared, and this would make a difference. The dark matter content is slightly less later on than earlier, and it could be an explanation for the Hubble tension, which is a bit of a puzzle to people, apparently. And if the dark matter decays, that would be one possible explanation. And so the bottom of this picture is what I'm agreeing to. As you go up the picture, gradually the dark matter disappears, and you just have gravitons. Crossover is sort of in the middle of the picture. I haven't put the line in there. It's sort of halfway across. That's where we've just got gravitons. The gravitons do carry through. And the top part of the picture I've drawn wrong, because it was some earlier theory I had. My theory now is more like the bottom picture the other way up. That is to say, you have gravitons coming together to produce dark matter. Now, what is the story here? The story is a bit like the story to some degree in the previous story. Let me go to the next slide. I think that's what I want. This is actually drawn for the earlier discussion, where you imagine the bottom of the picture is in the previous eon. Actually, the crossover is slightly, I don't know why I haven't drawn it in. It's between the bottom picture and the plane, which is probably last scattering surface, I think. This was drawn a long time ago, so I can't completely remember. Maybe it does say that. I'm not sure. Anyway, the fact is that you would get in the bottom picture, you have collisions between supermassive black holes. You see, what happens in the remote future? Mostly lots of maybe particles, electrons, which maybe decay into, well, the mass fades out, is what I'm saying. They don't decay. They just lose their mass eventually. That's part of the argument for, I won't go into that at the moment, but that is a reasonable conclusion in this picture, that the mass should fade out. But it takes an awful long to do it, long time. But the other strong feature, well, the dark matter produces gravitons, they decay into gravitons, so that's the background. You have quite a lot of gravitons coming from the decay of the dark matter. But the other part of the story are the galactic clusters. The galactic clusters produce enormously large black holes as they evolve, and the black holes run into each other from time to time and produce enormous explosions, producing enormous gravitational wave features coming out. And these gravitational wave features come through onto the other side And when they hit the background, they would produce more dark matter. So the dark matter would be produced in rings. Well, they would be spherical, things like spheres. I've drawn the picture so there are rings here, but there will be things like spheres, and our past light cone will intersect those spheres in what look like rings. So the argument would be that maybe Alexia's rings come about because you have the dark matter, which is already present, a sort of background dark matter, and then they're hit by these gravitons which come through from these events, which are enormous collisions between black holes, and these collisions produce spherical places where galaxies condense, and we intersect this with our past light cone and only see a ring's worth. You could get them concentric or almost concentric, because if you have a galactic cluster, black holes come together, and then maybe another black hole, and the black holes, when they collide, get a decent proper motion, probably because they spiral into each other in complicated ways. And then when they hit the next one, the center will be a little bit in a different place or with a different velocity. And so that means that the rings will not be quite concentric when they come through to the other side. But you might well get slightly concentric, but not quite rings of the sort that Alexei apparently sees, or does see. And this is a sort of explanation which I would claim that you might get. Thank you very much. I hope this has got through. I don't know, can I hear anything?
I will stop sharing.
Oh, I see. I can't hear anything. Can they hear anything? Did they hear my talk for a start?
Yeah, I think so. I think so. And so she's going to